There's a moment in Star Wars that everyone remembers, even if they've never seen the films. Luke Skywalker, standing on a desert world watching two suns set over the horizon. Twin points of light sinking together toward the dunes, painting the sky in doubled gold. It's one of cinema's most iconic images, and it captures something that speaks to us on a deep level. The strangeness, the beauty, the alien wonder of a sky with two suns instead of one. Tonight, we're going to explore that wonder. Not the catastrophe of losing our sun. We did that already, and it was rather bleak, wasn't it? But the opposite scenario, the abundance rather than absence, the complexity rather than simplicity. What if, instead of our solitary star faithfully burning alone in our sky, we had two? What if Earth orbited in a binary system with twin suns lighting our days and casting double shadows across the landscape? Hello, and welcome to the Sleepy Astronomer. If you're joining me for the first time, welcome to this gentle drift through cosmic possibilities. And if you've travelled with me before through impossible scenarios and stellar mysteries, it's wonderful to have you back for another thought experiment. Whether you're settling into bed, finding a comfortable spot on the couch, or perhaps lying somewhere you can almost imagine those twin suns overhead, I'm so grateful you're here to explore this question with me. If you enjoy these peaceful journeys through space and science, I'd be ever so grateful if you'd subscribe to join us for more cosmic explorations. And if this question intrigues you, a gentle like helps others discover these late-night wanderings through what-if scenarios. Here's the thing about binary star systems. They're not science fiction. They're not rare cosmic oddities. They're actually more common than single stars like our Sun. More than half of all star systems in our galaxy are binary or multiple star systems. Two stars, sometimes three or even more, orbiting each other in gravitational dances that have continued for billions of years. Out there in the universe, having one sun is almost, well, lonely, unusual. We're the odd ones out with our solitary star. So this isn't really a question of, what if something impossible happened? It's more like, what if we'd been born somewhere else? What if Earth had formed in one of those binary systems instead of around our single faithful sun? What would life be like? How would it be different? What would we gain and what would we lose? Tonight, we'll explore multiple scenarios, because there's no single answer to, what if we had two suns? It depends. Are they close together or far apart? Do we orbit both of them, or just one while the other shines from a distance? The possibilities create very different worlds, very different experiences, very different challenges and beauties. We'll discover what twin sunrises look like, how seasons work when you have two sources of heat instead of one, whether life could adapt to constant light or extreme temperatures, what human civilization might become under double stars, and ultimately what this thought experiment teaches us about the single sun we actually have, the one that will rise tomorrow morning, alone and perfect, just as it always has. So, find your most comfortable position, take a deep breath, and let yourself relax into this journey through doubled light and complex shadows. The question is simple. What if Earth had two suns? The answer is wonderfully complicated. Before we dive into imagining Earth with two suns, let's talk about just how normal that would be. Because when you look up at the night sky, you're looking at a universe that loves pairs. Binary star systems aren't exotic rarities. They're not cosmic accidents. They're actually the standard arrangement, and our single sun is somewhat unusual. We're the odd ones out, cosmically speaking. Think about that for a moment. More than half of all star systems in the Milky Way are binary or multiple star systems. That means that if you picked a random star out of the hundreds of billions in our galaxy, you'd have better than even odds that it has a companion. Two stars orbiting each other, bound by gravity, dancing around their common centre of mass in a partnership that often lasts billions of years. Some of these partnerships are obvious. Look at the constellation Cygnus, the swan, and find the star at the base of the swan's neck. That's Albireo. Even with a small telescope, you can see that it's not one star, but two, a golden-orange star and a sapphire-blue star, a stunning pair separated by enough distance that they're distinct and beautiful. They orbit each other slowly, majestically, taking thousands of years to complete one revolution. Or look at Sirius, the brightest star in our night sky. That brilliant point of light you see in winter is actually two stars. Sirius A, the bright one you can see, and Sirius B, a white dwarf companion that's invisible to the naked eye but orbits its brighter partner every 50 years. They're so close together, and Sirius B is so dim compared to its brilliant companion that ancient astronomers had no idea it was there. It wasn't discovered until 1862, when telescope technology finally got good enough to split the light and reveal the hidden partner. And then there's Alpha Centauri, the closest star system to our Sun, except it's not one star, it's three. Alpha Centauri A and B orbit each other in a relatively close dance, while Proxima Centauri, a small red dwarf, orbits much farther out. Our nearest stellar neighbours are a family, not a lone wanderer. So how do binary stars form? Why is the universe so fond of making stars in pairs? The answer goes back to stellar nurseries, those vast clouds of gas and dust where stars are born. When a region of the cloud begins to collapse under its own gravity, it doesn't always collapse into a single point. Sometimes the cloud has too much angular momentum, too much spin, and as it collapses, it fragments. Instead of one protostar forming, you get two. They form close together, in the same stellar nursery, from the same material, and they're born already in orbit around each other. It's rather like twins, actually. Born from the same parent cloud, emerging into existence at roughly the same time, bound together by gravity from their very first moments. They grow up together, age together, and in many cases they'll die together, or at least one will watch the other die, which is its own kind of cosmic tragedy. Binary stars come in many configurations, and this is where things get interesting for our thought experiment, because the configuration matters enormously for any planets that might exist in the system. There are close binaries where the two stars orbit each other in days or weeks. They're so close that they're essentially in a tight embrace, whirling around each other rapidly. Sometimes they're so close they actually share material, gas from one star flowing to the other in a stellar exchange that looks, from our perspective, like the stars are kissing. These are called contact binaries, and they're among the most extreme partnerships in the universe. Then there are wide binaries where the companion star is distant, hundreds or thousands of astronomical units away. These stars orbit each other slowly, taking centuries or millennia to complete one orbit. From the perspective of a planet orbiting one of them, the companion might just look like an unusually bright star in the night sky, a point of light that moves slowly through the constellations over the years. And there's everything in between. Medium separation binaries where the stars are close enough to significantly affect each other, but far enough to maintain their individuality. The variety is remarkable. The universe, given the basic ingredients of gravity and angular momentum, creates an astonishing diversity of stellar partnerships. Now here's something that might surprise you. We almost had two suns ourselves. Well, not quite, but close. Jupiter That giant planet in our solar system is often called a failed star, and there's some truth to that nickname. Jupiter is made mostly of hydrogen and helium, the same stuff stars are made of. It has its own miniature solar system of moons. It generates heat internally, more heat than it receives from the Sun, actually. In many ways, Jupiter is doing its best star impression. But it's not quite massive enough. To ignite fusion in its core, to become a true star, Jupiter would need to be about 80 times more massive than it is. That's a lot more mass. If you converted all the other planets, asteroids, comets, and miscellaneous debris in the solar system into Jupiter mass, you still wouldn't have enough. Jupiter would need to be about 1/10 the mass of the Sun to become even the dimmest, coolest type of star, a red dwarf. So we're not living in a binary system. We missed it by quite a margin. But it's interesting to think about, isn't it? If the early solar system had formed just a bit differently, if more mass had ended up in Jupiter's orbit during those chaotic early days, we might have had two suns. A proper sun and a small, dim companion. The solar system would be fundamentally different. We might not exist at all, or we might exist in a very different form, adapted to a reality with two sources of light and heat. But we don't. We have one sun, and that's shaped everything about us. Our biology, our culture, our sense of what's normal and what's exotic. When we look at binary systems, we're looking at something that's common in the universe but foreign to our experience. We're visitors imagining someone else's home. The physics of binary stars is elegant, really. Both stars orbit around their common centre of mass, the barycenter, which is the balance point of the system. If the stars are equal in mass, the barycenter is halfway between them, and they orbit like partners in a dance, neither leading, both moving together. If one star is much more massive than the other, the barycenter is closer to the heavier star. The massive star barely moves, just wobbles slightly, while its smaller companion sweeps out a large orbit around it. This is actually how we detect exoplanets, by the way. We watch stars for that telltale wobble, that slight motion that indicates something massive is orbiting them. Sometimes it's a planet, sometimes it's a brown dwarf, an object that's not quite a star but more than a planet, and sometimes it's another star that we couldn't see directly. Binary stars have been orbiting each other for as long as stars have existed. Some of the binary systems we observe today began their dance billions of years ago, when the universe was young and the Milky Way was still taking shape. They've been faithful to each other across timescales that make human civilization look like a brief flicker. They're reminders that the universe creates partnerships that last, bonds that endure across the deep time of cosmic history. So when we ask, what if Earth had two suns, we're not asking about something strange and impossible. We're asking about something that happens all the time, all across the galaxy, in stellar systems that are completely normal by cosmic standards. We're asking what it would be like to live in the majority situation rather than our minority single-star system. We're asking what it would be like to live somewhere else, somewhere that isn't exotic, isn't special, isn't unusual, somewhere that's actually quite ordinary, if you're looking at it from the universe's perspective. And the answer to that question depends entirely on the details. How far apart are the suns? How massive are they? How bright? Where does Earth orbit in the system? Because binary star systems come in so many configurations, there are many different possible experiences of having two suns. So let's explore them. Let's look at the different scenarios, from the least dramatic to the most extreme. Let's imagine what each would be like, how life would adapt, what would be beautiful, and what would be challenging. Let's visit these other worlds, not in space but in possibility, not physically but imaginatively. Let's see what the universe's most common stellar arrangement would feel like from the perspective of a small, rocky planet fortunate enough, or perhaps unfortunate enough, to orbit in such a system. Because binary stars are everywhere, and somewhere out there on a planet we haven't discovered yet, someone might be looking up at their two suns and imagining what it would be like to have just one. They might think we're the lucky ones, or they might think we're missing out. Let's find out which it is. Let's start with the gentlest scenario, the one that changes the least about our familiar experience. Imagine that our sun has a companion, a second star, smaller and dimmer, orbiting far out in the solar system. Not where Jupiter is, not even where Neptune is, but much farther, out beyond the Kuiper belt, beyond the scattered disk, in that distant realm where the sun's influence fades and interstellar space begins. This companion star, let's call it Sun B for simplicity, might be a red dwarf, one of those small, cool stars that burn their fuel so slowly they'll outlive every other type of star in the universe. Or perhaps an orange dwarf, somewhat larger and brighter, but still considerably smaller than our sun. The key thing is that it's distant. It takes hundreds of years, maybe thousands, to complete one orbit around our sun. From Earth's perspective, it's far away, a bright point in the night sky, moving slowly through the constellations like a planet, but brighter, steadier, unmistakably a star. This is the least dramatic of our scenarios, but it's also perhaps the most likely to actually support life as we know it. Earth continues to orbit our primary sun. Let's call it Sun A now, to keep things clear. At the same comfortable distance, one astronomical unit, 93 million miles, the perfect distance for liquid water, for moderate temperatures, for the conditions that allowed life to emerge and flourish. But now, in our sky, there's something extra, a second sun, distant but present. And that presence, even from far away, would change things in fascinating ways. Let's talk about seasons first, because this is where things get interesting. Right now, Earth seasons are caused by the tilt of our axis. As we orbit the sun, different hemispheres tilt toward or away from the sunlight, creating summer and winter. This pattern repeats every year, regular as clockwork, predictable to the day. We've built our entire agricultural civilization around this rhythm. Plant in spring, grow through summer, harvest in fall, rest in winter. It's been this way for thousands of years of human history. But add a second sun, even a distant one, and seasons become more complicated. Because now you have to consider not just Earth's position relative to Sun A, but also Sun B's position relative to both Earth and Sun A. And since Sun B takes centuries to orbit, its position changes very, very slowly. Over a human lifetime, it barely moves. But over generations, over centuries, its influence accumulates. When Sun B is on the same side of the solar system as Earth, when Earth is between Sun A and Sun B, or when Earth and Sun B are both on the same side of Sun A, we receive a little extra heat. Not much, because Sun B is far away and probably not very bright, but some. A few degrees of warming perhaps. Spread across decades or centuries, this creates what we might call a long summer. Not a season in the traditional sense, but a climatic period, an age of warmth that lasts longer than any human remembers. And when Sun B swings around to the far side of its orbit, when Sun A is between Earth and Sun B, we lose that extra warmth. The temperatures drop slightly, not catastrophically. We're talking about subtle changes, a few degrees averaged over years, but enough to matter. Enough that glaciers advance a bit farther. Snow lingers longer in spring. Growing seasons shorten slightly. This is the long winter, and it too lasts for lifetimes. If this sounds familiar, it's because George R.R. Martin got this exactly right in Game of Thrones. Winter is coming isn't just a motto in that world, it's astronomy. The unpredictable multi-year seasons in Westeros are precisely what you'd expect from a planet in a system with a distant companion star. Summers that last for years, winters that stretch across lifetimes, and the critical importance of preparing for changes that operate on timescales longer than individual memory. Human civilization in this scenario would need to think much more long-term. You can't just prepare for next winter. You need to prepare for the winter your grandchildren will experience. You need libraries, written records, institutions that preserve knowledge across generations. Remember, when the second sun was in Virgo, the Great Famine began. Watch the sky, keep records, prepare. Agriculture would be challenging. You couldn't rely on annual cycles alone. You'd need to track both the yearly seasons caused by Earth's axial tilt and the century-long cycles caused by Sun B's orbit. Farmers would become astronomers by necessity. The position of the distant sun in the sky would matter as much as the local weather. Is it approaching? Time to plant crops that thrive in warmth. Is it receding? Switch to hardier varieties that can handle the cooling. Navigation would be different too. Ancient sailors used the stars to guide them across oceans, tracking Polaris and the predictable movements of constellations. But in a system with a distant companion sun, you'd have an additional reference point, a bright star that moves, that shifts position over decades, that serves as both compass and calendar. When I was young, the second sun rose in Taurus. Now, in my old age, it rises in Gemini. Thus decades pass, measured in constellations. The night sky itself would be transformed. Most of the time, Sun B would be too far away to provide significant illumination. It would just look like an extremely bright star, much brighter than Venus at its most brilliant, but still a point of light rather than a disk. But even a point of light that bright changes things. You could read by it, perhaps, cast shadows, see colours at night instead of just shades of grey. And think about the symbolism, the mythology that would develop around two suns. In our world, the sun is often singular in our myths. Apollo driving his chariot, Ra sailing across the sky, Amaterasu emerging from her cave. The sun is the sun. But in a binary system, even with the companion distant, you'd have duality at the heart of your cosmology. Perhaps the suns are siblings, cooperative partners maintaining the world together. Perhaps they're rivals, competing for dominance, their relative positions explaining the long summers and winters. Perhaps one is the true sun and the other is an imposter, a pretender, a trickster. Or perhaps they're lovers, dancing across the sky, sometimes close, sometimes far, their relationship explaining the cycles of warmth and cold. The calendar would be magnificently complex. You'd need at least two systems, one tracking Earth's orbit around Sun A, the short year, essentially identical to our current year, and another tracking Sun B's position relative to the primary sun, the great year, lasting centuries. Important events might be dated like this. Born in the third month of the 847th short year of the approaching, in the age when the second sun wandered through Sagittarius. Imagine being a child in this world, looking up at the night sky and seeing that brilliant point of light. Your parents tell you it's a sun, like the one that warms your days, but far away. You watch it over the years of your childhood, and yes, it moves, slowly, perceptibly if you're patient. Your grandparents remember when it was in a different part of the sky. Your great-grandparents remember when it was farther still. The second sun becomes a marker of time, a reminder that change operates on scales larger than your own life. There's something both humbling and comforting about that, isn't there? The knowledge that the cosmos moves according to rhythms that dwarf your individual existence, but that you can still track those movements, understand them, predict them. You're small, but you're not ignorant. You're brief, but you're not blind. Art would be influenced by this duality. Paintings might show the landscape under the primary sun and again under the light of the distant companion. Two versions of the same scene, subtly different in mood and shadow. Poetry would play with themes of distance and closeness, presence and absence. My love is like the second sun, far but faithful, dim but constant, and oh, how I long for the century when she draws near. Music, too. Composers might create pieces in two movements, one for the age of warmth, one for the age of cold. Festivals would mark the slow progression of the companion star through the zodiac. The second sun has entered Scorpio becomes a holiday, a time of feasting and remembrance because your great-grandparents celebrated the same crossing, and your great-grandchildren will celebrate it again. And there would be those rare, precious moments when Sun B passes close to Earth's orbit. Not collision course close, remember, it's still orbiting the primary sun at a vast distance, but relatively close by the standards of its orbit. During these passages, which might happen once every few centuries, the second sun would appear brighter than usual. Perhaps bright enough to cast real shadows at night. Perhaps bright enough that midnight isn't quite so dark anymore, that true darkness becomes a rare gift. Imagine experiencing that. You're living in the long approach, and elders tell stories of the last time the second sun came this close. It was before your great-grandparents were born, but records exist, drawings, descriptions, and now, in your lifetime, it's happening again. Each night, the second sun grows fractionally brighter. Each month, its light becomes a bit more substantial. And finally, at its closest approach, you can see shadows at midnight. Two shadows, one from the primary sun if it's above the horizon, one from the companion if it's night. The world is bathed in light that's softer than day but brighter than any night you've known. And then it passes, begins its long recession. Your grandchildren will see it dimmer. Your great-grandchildren will know it only as that very bright star, but not the brilliant beacon you witnessed. And the stories will be told again. Records kept, knowledge preserved, preparing for the next approach centuries hence. Science would develop differently in this world. Astronomy wouldn't be about understanding a single central body that everything orbits. It would be about understanding a system with two centers, two sources of light and gravity, complex orbital mechanics that play out over time scales longer than individual lives. This might actually accelerate scientific understanding. When the evidence of complex celestial mechanics is written across your sky, visible to anyone who looks up and pays attention over decades, the questions become unavoidable. Why does the second sun move through the constellations? How far away is it? Why do the long summers come? These aren't abstract questions for specialists. They're practical matters that affect agriculture, navigation, timekeeping. Everyone needs some understanding of orbital mechanics, even if they don't call it that. The shepherd watching stars, the farmer planting crops, the sailor crossing seas, they all need to understand the dance of the two suns. There would be schools dedicated to this knowledge, astronomers who spend lifetimes tracking the slow movements, updating the models, refining the predictions, not for academic interest alone, but because the information is vital. Knowing when the long winter will deepen, when the long summer will warm, this determines whether your civilization thrives or struggles. And there would be debates, surely, different schools of thought about what causes the movements. religious explanations versus naturalistic ones, the correct mathematical model for predicting the second sun's position, controversies that span generations, with each side marshalling observations, keeping records, building instruments to track the distant companion with ever greater precision. In many ways, this scenario is the most realistic for actually having an Earth-like civilization. The changes are significant enough to matter, to shape culture and knowledge and myth, but not so extreme that life becomes impossible. Humans could adapt to this. We could thrive in this. It would make us different, certainly. Our sense of time would be longer. Our mythology would be built around duality. Our science would be forced to grapple with complex orbital mechanics earlier in our development. But we'd still be recognizably human. We'd still farm and build and love and create art and ask questions about the cosmos. We'd still look up at the sky with wonder, though what we'd see would be different from what we see now. We'd have two lights in our cosmology, two markers of time, two partners in the celestial dance. One sun close and warm, the daily companion, the giver of light and life. One sun distant and cool, the patient witness, moving through the ages, marking time on scales that humble individual ambition, but inspire collective endeavour. And we'd learn to live with both, to appreciate the constancy of the near and the mystery of the far, to understand that the universe operates on multiple scales simultaneously, the daily, the yearly, the generational, the epochal, and that wisdom means respecting all of them. This is the gentlest of our scenarios, the one where Earth keeps its comfortable orbit and gains only a distant companion. No extreme temperatures, no impossible conditions, just more complexity, more to track, more to understand, more to inspire wonder. And perhaps that's enough. Perhaps having two suns doesn't need to be catastrophic or alien to be profound. Perhaps just adding that distant point of light, that second marker in the sky, that slow-moving reminder of deep time, would be sufficient to change everything about how we see ourselves and our place in the cosmos. This is what a distant companion gives you, perspective. A reminder that time moves on scales larger than your life, that patience is measured in centuries, that faithfulness means tracking movements you won't live to see complete. It's a gentle lesson, but a profound one, and it's the most survivable of our scenarios, which is why we started here. The easy one, the one where life continues, recognizable but different, familiar but strange. But we're not done. We have other scenarios to explore, closer configurations, more dramatic arrangements, situations where the presence of two suns isn't a subtle influence but a dominating fact of existence. Let's continue our journey. Let's move the suns closer together and see what happens. Because while a distant companion is beautiful and manageable, it's not what most people imagine when they picture a world with two suns. They imagine Tatooine, twin suns in the sky, both visible as disks, both bright, both significant. So let's go there next. Now, let's move to the scenario that lives in popular imagination, the one that Star Wars showed us, that science fiction has explored countless times, that feels both alien and somehow right when you picture it. Two suns in the sky, both visible as actual disks, both contributing significant light and heat, orbiting each other closely enough that Earth orbits around both of them. This is called a circumbinary orbit, and yes, it's a real thing. We've actually discovered planets that orbit this way, Kepler 16b being the most famous, the genuine Tatooine, a gas giant circling two stars that orbit each other every 41 days. So we're not imagining something impossible here. We're imagining something that exists out there in the universe, possibly with its own story of life and adaptation, and creatures looking up at their twin suns, wondering what it would be like to have just one. Let's set up our scenario. Imagine two stars orbiting each other relatively closely. Maybe they complete one orbit every few weeks or months. Neither is as large as our current sun. Perhaps one is a bit smaller, an orange dwarf, and the other smaller still, a large red dwarf. Together, they put out roughly the same amount of energy our sun does, but from two sources instead of one. Earth orbits both of them at a distance that keeps us in the habitable zone. Not too hot, not too cold, at least on average. This orbit might take somewhat longer than our current year, or about the same depending on the exact configuration. The key thing is, we're orbiting a binary system. Two stars that orbit each other, and we orbit them both. This is where things get beautifully complicated. Let's start with the most basic question. What does the sky look like? Well, that depends on where Earth is in its orbit, and where the two stars are in their orbit around each other, and what time of day it is. This isn't a simple answer anymore. The sky becomes dynamic in ways we never experience with our single sun. Sometimes both suns are above the horizon together. This is the brightest time, what we might call high day. The sky would be intensely bright, not quite twice as bright as our current noon, because the suns aren't positioned to perfectly add their light, and one is probably dimmer than the other, but noticeably, significantly brighter than anything we experience. Colours would be vivid, shadows would be complex. You'd cast two shadows, one from each sun, and where those shadows overlap, you'd get deeper darkness. Sometimes one sun is up while the other is down. This is still day, but it's dimmer. More like what we'd consider morning or late afternoon light, even if it happens to be the middle of the day by clock time. You'd have one shadow cast by one sun, and the quality of light would depend on which sun is up. If it's the orange dwarf, you'd have warmer, more golden light. If it's the red dwarf, cooler, more amber tones. And sometimes, rarely briefly, both suns are below the horizon. This is night, actual night, darkness, stars visible, the moon, if it's up, as the brightest thing in the sky. These periods are precious, rare enough that you'd plan around them. Let's meet when both suns are down becomes a romantic notion, because darkness is so unusual, so special. The concept of a day becomes complicated. Do you measure a day by Earth's rotation? That still takes 24 hours, roughly. But day and night no longer correspond neatly to that rotation. You might experience high day, then medium day, then low day, then a brief night, all within one rotation of Earth. Or you might have continuous daylight of varying intensity for several rotations before finally getting a night. Timekeeping would need to account for this complexity. You'd probably keep Earth rotation time, call it local time, for daily scheduling, but you'd also track the positions of both suns. Meeting at 3 local during high day, when both suns are in the east. You'd need to specify not just the hour, but the lighting conditions, because they're not predictable from the hour alone. Sunrise and sunset become extraordinary events. Sometimes one sun rises while the other is already up, double dawn, a brightening that happens in stages. Sometimes one sun sets while the other is still above the horizon, a sunset that doesn't lead to night but just a dimmer day. And sometimes, gloriously, you get both suns rising or setting together, though not quite at the same point on the horizon because they are orbiting each other. Twin dawn, twin dusk, the sky painted in doubled gold. There would be times, depending on the orbital configuration, when one sun eclipses the other from Earth's perspective. Not a total eclipse like our moon creates. We're talking about one sun passing in front of its companion. Depending on their relative sizes, you might see a partial eclipse, where the smaller sun takes a bite out of the larger one, or if they're similar in size, you might see one sun completely covering the other, creating a strange period where there's only one sun in the sky instead of two. These events would be tracked carefully, predicted, marked as significant moments in the calendar. The temperature variations would be significant, but not catastrophic, assuming we're in the right orbital distance. When Earth is closer to the binary pair in its orbit, we'd receive more heat. This is summer, but it's a summer defined by orbital distance, not by axial tilt. When we're farther from the pair, winter. These seasons would be more extreme than what we experience now, but life could adapt. But there's another layer of temperature variation, the orientation of the binary stars relative to Earth. When both stars are on the same side of Earth, when it's high day and both are above the horizon together, we're receiving maximum radiation. When the stars are on opposite sides of Earth, one rising as the other sets, the heat is more evenly distributed over the planet. This creates a kind of micro-season within each Earth rotation, a pulse of heat and cooling that happens daily rather than yearly. Plants would have a very interesting time of it. Photosynthesis depends on light, obviously, but plants have evolved to expect certain patterns. Dark periods for rest and repair, consistent daily cycles. Our plants might struggle in this environment where night is rare and day comes in varying intensities. But life adapts. In this scenario, plants might evolve to be darker, not green. Why? Because they'd need to reflect more light, not capture it all. Too much light can damage chlorophyll, can overwhelm the photosynthetic machinery. Plants on a circumbinary planet might be black or very dark purple or deep red, absorbing only the wavelengths they need and reflecting the rest. This would make forests look alien to our eyes. Imagine dark violet leaves, nearly black trunks, a landscape that looks like it's in permanent shadow, even under brilliant double sunlight. Or perhaps plants would evolve movable shade, leaves that can curl up or reposition themselves to reduce light exposure during high day, then open fully during medium or low day to maximize collection when light is less intense. Picture a forest that visibly responds to the changing light, leaves adjusting throughout the day, the whole landscape in subtle motion. Animals would need to adapt to inconsistent day-night cycles. Our circadian rhythms, our internal clocks, are tuned to a predictable 24-hour cycle of light and dark. But on a circumbinary planet, that prediction breaks down. Sometimes you have brief night. Sometimes you have continuous moderate daylight for days. Sometimes you have periods of intense brightness. Animals might evolve to be polyphasic sleepers, sleeping in multiple short periods rather than one long stretch. Or they might split into distinct populations, some active during high day, some during medium day, some during the rare nights. Ecological niches defined not just by what you eat, but by when you're awake. Birds would probably do fine, actually. Many bird species already have flexible sleep patterns and can adjust to varying light conditions. They might be the most successful large animals in this scenario. Mammals, with our more rigid sleep requirements, would face more challenges. We'd probably evolve to be more flexible, to handle sleep deprivation better, to function with interrupted rest. Humans, or human-like intelligent beings, living in this system would have a very different relationship with sleep. The concept of bedtime wouldn't mean much when night comes at unpredictable intervals. You'd sleep when both suns are down, which might happen at midday or midnight or not at all for several days. Or you'd learn to sleep in bright light, developing cultural norms around sleep chambers, blackout rooms, artificial night. The architecture would be fascinating. Buildings would be designed with shade in mind, with ways to block or filter the intense light of high day, deep eaves, shuttered windows, reflective surfaces to redirect light. Perhaps buildings would be partially underground, using the earth itself as insulation and light control. Or perhaps structures would be mobile, capable of reorienting themselves to maximize or minimize solar exposure depending on the time and season. Culturally, this would shape everything. Art would play with complex shadows and multiple light sources. Painters would need to master the different qualities of light, the warm glow of high day, the amber of single sun periods, the rarity of starlit night. Photography would be an advanced art, requiring sophisticated understanding of multiple exposures and overlapping light sources. Fashion would be practical, clothing designed for sun protection, hats, veils, reflective garments, or perhaps the opposite, minimal clothing because it's always warm, with a culture normalizing near nudity as the practical response to constant heat. Body modification might be common, tattoos or skin treatments that increase reflectivity, parasols or fans as ubiquitous accessories. The mythology would be rich. 2 suns, both visible, both clearly important to life. They'd need names, they'd need stories. Perhaps they're partners working together to sustain the world. Perhaps they're rivals, competing for dominance. Perhaps they're parent and child, elder and younger, teacher and student. The stories would explain why sometimes they appear together and sometimes apart, why sometimes one eclipses the other, why the light varies. There might be festivals tied to the rare moments of true night. The Darkness Festival, when both suns finally set together, and for a few precious hours the world experiences what their ancestors knew: stars, moon, the profound quiet of night. These would be sacred times, times for reflection, for ceremony, for experiencing something so unusual it feels supernatural. Navigation would be complicated. You couldn't rely on the sun's position to tell direction, because there are 2 suns and they're moving relative to each other. You'd need to track both positions, understand their dance, and calculate from that. Or you'd rely more heavily on stars, using those rare night periods to take accurate readings, mapping your world by the fixed points rather than the moving ones. Science would develop along different paths. The obvious complexity of having 2 suns orbiting each other would make orbital mechanics immediately apparent. You couldn't mistake this for a geocentric universe. The suns clearly orbit each other, and careful observation would show that Earth orbits them both. This might accelerate the development of physics, astronomy, mathematics. When the evidence of complex gravitational dynamics is written across your sky multiple times per day, you can't help but try to understand it. But it might also make some things harder. Studying other planets in your system would be challenging, because they're all moving in response to 2 gravitational sources. Predicting eclipses of the suns, of moons, of planets would require sophisticated mathematics. The astronomy of a circumbinary system is genuinely more complex than what we deal with. There would be practical challenges we don't face. Solar panels would need to track 2 suns, or be designed to capture light from multiple angles. Agriculture would require understanding not just seasonal cycles, but the multiple overlapping cycles of orbital distance, stellar orientation, and Earth's rotation. Water management would be crucial because evaporation rates would be high during extended periods of double sunlight. Heat management would be the central technological challenge. How do you keep cool when you're receiving light from 2 sources for most of the time? Refrigeration becomes not a luxury, but a necessity. Architecture evolves around heat dissipation. Clothing, food storage, social norms. everything shaped by the constant presence of light and heat. And yet, people would adapt. They'd find solutions. They'd build homes that stay cool, create clothing that protects, develop schedules that work with the lighting patterns rather than against them. They'd create beauty in their art and meaning in their myths and understanding through their science. Children would grow up never knowing the simplicity of one sun rising and setting with perfect predictability. They'd learn to read a more complex sky, to understand a more intricate dance. They'd develop intuition for when both suns would be up together, when one would set, when the rare night might come. It would be normal to them, the way our single sun is normal to us. And perhaps they'd look at their complex sky and find it beautiful. Two lights instead of one, patterns within patterns, shadows that dance and shift, a day that's never quite the same as the previous day, variety, complexity, constant change. We might call it chaos, they might call it richness. There's a certain elegance to it, isn't there? The way the universe takes the same basic ingredients, gravity, light, mass, and creates such different experiences depending on the configuration. A distant companion gives you one kind of world. A close binary gives you this, brighter, hotter, more complex, more challenging, but not impossible. Not uninhabitable, just different. Life finds a way, as they say, and intelligence, once it emerges, finds ways to understand and adapt and create meaning from whatever circumstances it's born into. A species that evolved in a circumbinary system wouldn't think of themselves as living in a difficult environment. They'd think of it as normal, as home. The twin suns would be as fundamental to their identity as our single sun is to ours. They'd have sayings about it, as constant as the changing suns. Between one sun and another, wait for the darkness, meaning be patient, because good things come to those who wait for rare events. Their idioms would be different from ours because their experience is different. And if they ever looked up at the night sky during those precious dark hours, if they developed telescopes and studied other star systems, they might discover something surprising. They might find that single star systems are common too. They might look at our solar system and think, how strange, how lonely, just one sun all by itself. I wonder what that's like. I wonder if anyone lives there, orbiting that solitary star. They might imagine us the way we're imagining them. They might wonder what it's like to have such simple, predictable light, to have one sunrise, one sunset, one clear distinction between day and night. They might think we're lucky, or they might think we're missing out on something beautiful. This is the Tatooine scenario. This is the world of twin suns visible in the sky, of complex shadows and rare darkness, of life adapted to abundance of light rather than scarcity. It's more extreme than the distant companion, but still potentially habitable. Still a place where life could emerge, intelligence could evolve, civilization could build. But we have one more scenario to explore, one more configuration of two suns, and this one is the most extreme, the most chaotic, the most unlikely to support life, but the most fascinating to imagine. What if Earth didn't orbit both suns in a stable ring? What if, instead, we traced a figure-8 pattern between them, pulled by both gravitational sources, never quite settling into predictability? That's where we're going next, into the chaos, into the ultimate expression of what two suns could mean. Let's see what happens when stability gives way to dynamism, when the dance becomes too wild, when having two suns stops being a challenge and becomes an impossibility. Or does it? Let's find out. Now, let's get truly chaotic. Let's imagine something that orbital mechanics would probably forbid if we looked at it too closely, but that's fascinating enough to explore anyway. What if Earth didn't orbit both suns in a stable circle, or just one sun while the other stayed distant? What if, instead, Earth traced a figure-8 pattern between two stars, passing close to one, then swinging across to pass close to the other, then back again, forever caught between two gravitational sources, never quite settling into the comfortable predictability of an ellipse? This is almost certainly unstable on geological timescales. The math of three-body problems, two stars and a planet all influencing each other gravitationally, is notoriously complex. Most solutions eventually end with the planet either being ejected from the system entirely or crashing into one of the stars. Stable orbits exist, but their specific configurations, special cases. A figure-8 orbit is not one of those special cases. It's dynamically unstable, meaning that over time, probably not very much time, something would go wrong. But let's imagine it anyway. Let's say Earth is somehow locked into this dance, at least temporarily. Maybe it'll only last a few million years before the system destabilizes, but a few million years is plenty of time for life to exist, for evolution to work, for interesting things to happen. And if we're being generous with our imagination, and we are because this is a thought experiment, maybe there's some configuration we haven't thought of where this could be semi-stable for longer. So, Earth in a figure-8 orbit between two suns, what would that actually be like? The first thing to understand is that distance from a heat source matters enormously. Double the distance and you receive 1/4 of the energy. Halve the distance and you receive 4 times the energy. This is the inverse square law, and it's relentless. So as Earth swings closer to one star, then away, then closer to the other, then away again, the amount of solar radiation we receive would vary dramatically. Let's trace one complete cycle. Imagine Earth starting at the midpoint between the two stars. Let's call them star A and star B. We're receiving moderate heat from both, roughly equal amounts. The temperature is comfortable, maybe similar to what we experience now. This is the neutral zone, the brief period when things are balanced. But we're not stationary. We're moving, pulled by gravity, tracing that figure-8 path. We begin falling towards star A. As we approach, the heat increases. Not gradually. Remember, it's following that inverse square law. As we get half as far away, the heat from star A quadruples. The temperature rises rapidly. Within weeks or months, depending on our speed, we go from comfortable to warm, to hot, to scorching. At closest approach to star A, we might be receiving several times more radiation than Earth normally gets. The temperature spikes, oceans begin to evaporate, ice caps, if they still existed from the previous cooling period, melt entirely. The atmosphere heats up, becomes turbulent. Weather patterns go haywire. It's not quite hot enough to boil the oceans away entirely, at least not in the configuration we're imagining, but it's hot enough to make most of the planet uncomfortable for life as we know it. And then we swing past. Having made our closest approach to star A, we're now heading away back toward the midpoint. The heat decreases as rapidly as it increased. Within weeks, we're back to moderate temperatures. Within more weeks, we're actually getting cool because we're moving away from star A faster than we're approaching star B. We pass through the midpoint again, that neutral zone where both stars are equidistant, and then we start falling towards star B. The same process happens again. Gradual approach, rapid heating, closest pass with maximum temperature, then swing away and cool down, back through the neutral zone, back towards star A. The cycle repeats. How long would one complete figure-8 take? That depends on the size of the orbit and the masses of the stars, but let's say something like 1 Earth year for argument's sake. You'd experience 2 intense summer periods, 1 near each star, and 2 moderate periods as you pass through the midpoint. but calling them summers doesn't quite capture the extremity. These aren't pleasant warm seasons. These are survival challenges. Life in this scenario would need to be incredibly adaptable. Let's think about what that means practically. Plants couldn't maintain permanent root systems in any one location because the climate varies too much. A spot that's moderate when Earth is at the midpoint becomes a desert when we're near star A, then freezes when we're far from both stars, then bakes again when we approach star B. No plant could handle that range of conditions in one location. But maybe plants could migrate. Imagine species with mobile seeds or spores that travel on the wind or water, establishing themselves quickly during the brief moderate periods, growing frantically, reproducing, then dying as conditions become extreme again. The whole planet would be in constant succession, with different species dominating different parts of the climate cycle. Or perhaps life would be primarily aquatic. Oceans are thermal buffers. They heat and cool much more slowly than land. The deep ocean especially would maintain relatively stable temperatures even as the surface world goes through extreme swings. Life might retreat to the depths during the hottest and coldest parts of the cycle, emerging only during the moderate periods. Animals would need to be mobile, migrating constantly to follow the narrow band of comfortable temperatures. As Earth approaches star A, you'd migrate toward the poles or underwater to escape the heat. As we swing away and temperatures drop, you'd migrate toward where star B's influence is growing, staying in that moving zone of moderation. It would be a planet of nomads, of creatures that never settle, always on the move. Or alternatively, life might evolve to hibernate through the extreme periods. Imagine animals that can enter a dormant state, like tardigrades or desert frogs, when conditions become too hot or too cold, then revive during the brief windows when the climate is survivable. They'd need to be able to shut down their metabolism almost completely, survive months of extreme conditions, then wake up and function normally. This is possible. Earth has creatures that do similar things, but it would need to be the default strategy for most life, not an occasional adaptation. For humans, or any intelligent species, living in this system would be an exercise in constant adaptation. You couldn't build permanent cities because the climate where you build would become uninhabitable within months. Everything would need to be mobile, or so heavily fortified that it could withstand both extreme heat and extreme cold. Perhaps civilization would be nomadic, entire cities on wheels or ships migrating around the planet following the comfortable zones. Summer wouldn't mean a season. It would mean danger, the approach to one of the stars, time to pack up and move. Communities would become expert at disassembly and reassembly, at transporting everything they need, at living in transit. Or perhaps civilization would go underground, building deep bunkers that use the planet's thermal mass as insulation. When the surface world becomes too hot, you seal the hatches and wait it out underground where temperatures are moderated by miles of rock. When it becomes too cold, same strategy. You only emerge to the surface during the brief, moderate periods to gather resources, to see the sky, to remember what unfiltered sunlight feels like. The sky itself would be a constantly changing spectacle. As you approach star A, it grows larger in the sky, brighter, more dominant. Star B becomes a distant point, barely noticeable against star A's glare. Then you swing past, and star A shrinks, dims, becomes less significant. For a brief time, both stars are roughly equal in the sky, the midpoint passage, the moment of balance. Then star B grows as you approach it, becoming the dominant feature, overwhelming its companion. You'd never have predictable day and night. The day when you're near a star is intensely bright, overwhelming, inescapable. The night when you're between stars, those brief periods when you're far from both, would be darker than any night we experience, because neither sun is close enough to dominate. The stars themselves would be visible, but faint. It would be a true dark night, precious and rare. Navigation would be nearly impossible using the suns. They're always changing position, always moving relative to Earth in unpredictable seeming ways. You'd need to rely on stars, on careful map-making, on technology. This would either accelerate the development of sophisticated navigation tools or make long-distance travel nearly impossible. Agriculture would be, well, let's be honest, agriculture as we know it would be impossible. You can't plant crops when the climate swings from hot to cold to hot again within a year. But perhaps you could have hydroponic systems, underground farms lit artificially, where climate is controlled regardless of what's happening on the surface. Food production would need to be divorced from the natural world entirely, a purely technological endeavour. The calendar would be straightforward in one sense. One complete figure 8 is 1 year, but complex in another. You'd need to track your position in the orbit carefully, because that determines everything about your current conditions and immediate future. We're at the far point from star A. Approaching star B tells you more than any date could. It tells you the weather, the migration schedule, the harvest timing from underground farms, the safety protocols. There would be stories, of course, myths to explain why the world is the way it is. Perhaps the two stars are gods locked in eternal conflict, and Earth is the battlefield. Perhaps they're lovers who can never unite, and Earth is their child, passed between them, never quite belonging to either. Perhaps the figure 8 orbit is a dance, a ceremony, a cosmic ritual that Earth must complete to maintain balance in the universe. Philosophy would likely be shaped by impermanence. Nothing lasts, nothing stays. The climate changes, the landscape transforms. What was comfortable becomes hostile, becomes comfortable again. The only constant is change. This might create a culture that values adaptability over stability, flexibility over permanence, journeys over destinations. Science would develop along fascinating paths. The figure 8 orbit would make orbital mechanics immediately, viscerally obvious. You can't mistake what's happening when you're swinging between two stars, and the effects are that dramatic. But predicting the exact path, calculating future positions, understanding the three-body dynamics, that would require advanced mathematics much earlier than human civilization developed it. Survival would depend on accurate predictions, and there would be awareness always that this is temporary. Whether through scientific understanding or intuitive cultural knowledge, inhabitants would know that the orbit is unstable, that someday, maybe in 1,000,000 years, maybe sooner, Earth will either be flung out into interstellar space or crash into one of the stars. The world has an expiration date. Not an abstract, the sun will eventually die billions of years away, but a more immediate, this configuration cannot last. How does that shape culture, religion, long-term planning? Perhaps it creates urgency, a drive to accomplish things, to create, to leave a mark before the end comes. Perhaps it creates fatalism, a sense that nothing matters because it's all temporary anyway. Or perhaps, and this might be more likely, it creates balance, an acknowledgement that yes, everything ends, but we're here now, and that's what matters. We adapt, we survive, we find beauty in the moment, because the moment is all we have. The engineering challenges would be immense. Heat management during close approaches, insulation during distant periods. materials that can withstand thermal cycling, structures that won't crack from expansion and contraction, water storage systems that work whether H2O is ice, liquid, or vapor, energy generation that functions in varying sunlight conditions. But humans are good at engineering. We solve problems, we build things. And if we evolved in this system, if this was our normal, we'd have millions of years of evolutionary pressure creating adaptations we can barely imagine. Heat tolerance, cold tolerance, flexible metabolism, the ability to enter dormancy, whatever it takes to survive. The beauty of this scenario, despite its extremity, is that it shows the outer limits of what having two suns could mean. It's not just twice the light or twice the warmth. In specific configurations, it's chaos. It's instability made manifest. It's a world that refuses to settle into any pattern we'd recognize as comfortable. And yet life might exist anyway, might thrive even in its own way, might look at its figure 8 sky and find it normal, might wonder what it would be like to have a stable orbit, predictable seasons, a sun that stays roughly the same distance away all year. Might think that sounds boring. We can't know. What we can know is that this represents the extreme of possibility. If there's a planet in a figure 8 orbit somewhere, and there probably isn't, but the universe is large and strange, it would be the most challenging place to live that we've imagined so far. Not impossible, just very, very hard. But the universe doesn't care about hard. The universe just follows the math. And if the math says a planet can exist in a figure 8 orbit, even temporarily, then somewhere, sometime, it might have happened. Might be happening now. Might happen in the future. And if life arose there, if intelligence evolved there, if someone is standing on that world right now, feeling the heat building as they approach one of their stars, knowing they have weeks before they need to migrate or go underground, what are they thinking? Are they cursing their fate, wishing for stability? Or have they found beauty in the chaos, meaning in the impermanence, purpose in the constant adaptation? We'll never know, but it's worth imagining, worth exploring, worth understanding that two suns can mean many things, from the gentle, distant companion to this wild figure 8 dance, and that life, stubborn and creative and remarkably flexible, might find a way in any of them. This is the extreme scenario, the chaotic one, the unlikely one. But having explored it, having pushed the concept of two suns to its limits, we can now ask better questions about what's actually out there, about the circumbinary planets we've discovered, about what life might look like when the sky contains multiple stars. Let's pull back now. Let's look at what we know rather than what we imagine. Let's talk about real exoplanets in binary systems, about what we've learned and what we're still trying to understand. Because the universe is showing us that yes, planets can orbit twin stars. Yes, life might exist in these systems. And yes, somewhere out there, someone might be looking up at two suns and dreaming of what it would be like to have just one. Let's find out what's real. We've explored the scenarios, the configurations of two suns, the orbital mechanics, the physics of doubled light. But now let's talk about life itself. Not just survival, not just adaptation, but the fundamental ways that biology would be different under twin stars. Because life shapes itself to fit its environment, and an environment with two suns would shape life into forms we might not recognize, creating solutions to problems we don't face. Let's start with the most fundamental biological process on Earth, photosynthesis, the conversion of light energy into chemical energy, the foundation of nearly every food chain, the process that produces the oxygen we breathe, the reason our world is green. Except, Would it be green under two suns? Here's the thing about photosynthesis. It's optimized for our sun's light spectrum. Chlorophyll, the pigment that makes plants green, is green because it reflects green light. It absorbs red and blue wavelengths, uses that energy to power chemical reactions, and bounces back the green that it doesn't need. This works perfectly for our sun, which produces plenty of red and blue light. But two suns, especially if they're different types of stars, would produce a different mix of wavelengths. And if those suns are putting out more total light than Earth's plants evolved to handle, chlorophyll has a problem. Too much light can damage the photosynthetic machinery. It's like overloading an electrical system. You need to dissipate the excess or things break. So plants might evolve to be darker, not lighter. Black plants, dark purple plants, deep red plants that look almost brown. These colours would absorb only the light they need and reflect the rest, preventing damage from too much solar radiation. Imagine a forest where the leaves are nearly black, where the undergrowth is dark violet, where nothing is the vibrant green we associate with life. It would look alien, almost lifeless, until you realize that this darkness is itself a sign of life adapting to abundance. Or plants might evolve reflective surfaces, silvery leaves that mirror back most of the light, absorbing only a tiny fraction. Picture a meadow that glitters like it's covered in metal, plants that look like they're coated in chrome, a landscape that's almost painful to look at under double sunlight because of all the reflected glare. It would be beautiful in its own strange way, but nothing like what we know. Another possibility, plants might develop movable parts specifically for light management, not just the simple turning that sunflowers do, following one sun across the sky, but complex folding mechanisms, leaves that can curl up like umbrellas during the brightest periods, exposing less surface area. Petals that can close to protect delicate structures, a forest that visibly responds to light intensity, constantly adjusting, always in subtle motion. Some plants might abandon surface life entirely. Underground photosynthesis sounds impossible. You need light after all. But maybe you'd have plants with extensive above-ground mirror systems that reflect light down into underground chambers, where the actual photosynthetic tissue is protected from direct exposure. It's complicated, probably less efficient, but evolution works with what it has. If surface life is too harsh, life goes underground and finds a way. Now let's talk about animals, because they'd face their own challenges in a double-sun world. Eyes would need to be different. Our eyes are designed for the light levels we experience on Earth. The iris adjusts to control how much light enters. The retina has cells optimized for our specific range of brightness. But under two suns, especially during periods when both are overhead, light levels could be intense enough to overwhelm our visual system. Animals might evolve much narrower pupils, like a cat's slit pupil, but even more extreme, or multiple layers of protection, eyelids that are partly transparent, letting some light through even when closed so you can still navigate with your eyes shut against the glare, or nictitating membranes that are essentially built-in sunglasses, sliding across the eye to filter light when needed. Some animals might abandon daytime vision almost entirely. Why compete in the overwhelming brightness when you can specialize in the rare darkness? Nocturnal animals would have a significant advantage. During those brief periods when both suns are down, they'd be the only ones who can see well. The rest of the ecosystem would be nearly blind in actual darkness, their vision optimized for brightness. Nighttime predators would rule those precious dark hours. Or perhaps eyes would evolve to see in different wavelengths. Infrared vision might be more useful than visible light vision when your environment is flooded with visible light anyway. or ultraviolet sensitivity, the ability to see in wavelengths that are less saturated, where you can still distinguish details even when visible light is overwhelming. Heat management would be crucial. Animals on Earth dissipate heat through various methods: sweating, panting, large ears that act as radiators, behavioral adaptations like seeking shade. But in a world with two suns, and potentially much more heat, these mechanisms might not be enough. You might see animals with extremely large surface area to volume ratios. Think of elephant ears, but more extreme. Animals with massive wings or fins or membranes that serve primarily as heat radiators. Or perhaps animals that are very thin and tall, maximizing surface area for cooling while minimizing volume. Or you might see the opposite, animals that are underground dwellers by day, emerging only at night or during single sun periods. Burrowing as the default lifestyle. This would create a strange ecosystem where the surface world seems nearly empty during the brightest times, then explodes with activity when conditions moderate. Water retention would be critical. More sun means more evaporation, both from the environment and from animals themselves. You'd expect to see desert adaptations as the norm rather than the exception. Thick, waxy skin to prevent moisture loss, concentrated urine, behavioral adaptations like estivation, sleeping through the hottest periods, sealed in a moisture-conserving cocoon. Some animals might be primarily aquatic, using water as both shield and cooling system. The ocean, with its thermal inertia, would be the most stable environment. Marine life might flourish while terrestrial life struggles. You could have a world where most large animals are oceanic, where the land is the extreme environment and the sea is the refuge. Circadian rhythms would be fascinating. Our bodies run on roughly 24-hour cycles synchronized to the day-night pattern. But in a world where day and night don't follow predictable patterns, where sometimes you have continuous light for days, sometimes brief nights, sometimes variable intensity, how does biology keep time? Animals might evolve to be polyphasic sleepers, sleeping in short bursts whenever conditions are favorable rather than in one long stretch. Or they might have flexible circadian rhythms that can adjust to varying light patterns, shortening or lengthening as needed. Or perhaps they'd abandon circadian rhythms entirely, sleeping based on fatigue and activity rather than time of day. This would create interesting ecological niches, some species active during high light periods, some during medium light, some during rare darkness, some species with flexible activity patterns, able to function at any time. The competition wouldn't just be for food or territory, but for temporal niches. When you're active, what light conditions you're adapted to. Migration patterns would be extreme, not seasonal migration like birds flying south for winter, but continuous migration following comfortable conditions. As Earth's orbit brings it closer to one sun, animals migrate to stay in the habitable zone. As it swings toward the other sun, they migrate again. The whole biosphere in constant motion, never quite settling. This would favor species that can cover large distances efficiently. Flying animals would have an advantage. Fast runners, strong swimmers, anything that can move quickly and cover ground. Sedentary species would struggle unless they could survive extreme temperature swings. Evolution itself might operate differently. With more environmental variability, there's more selection pressure for flexibility and adaptability. You might see more generalist species rather than specialists, more behavioral plasticity, more capacity for rapid evolutionary change, a biosphere that's constantly in flux, where no adaptation is permanent because the environment keeps shifting. There's also the question of how intelligence might evolve in such a world. On Earth, intelligence seems to be favored in environments that are challenging but not impossible. Places that reward problem-solving, planning, social cooperation. A world with two suns, especially in a more chaotic configuration, is definitely challenging. But is it too challenging? Does the constant need to migrate, to manage heat, to find the rare comfortable conditions leave enough spare energy for developing large brains? Maybe intelligence evolves specifically to solve the problems that two suns create. Navigation becomes crucial, so spatial intelligence develops. Predicting orbital positions and climate changes becomes important, so pattern recognition and future planning develop. Communication becomes vital for coordinating migrations, so language evolves. The challenges of the environment become the driver for cognitive complexity. Or maybe intelligence evolves in aquatic species, where the environment is more stable and there's more energy available for big brains. Maybe the seas are where civilization emerges, while the land remains the harsh frontier. If humans, or something human-like, evolved in a binary star system, we'd be physiologically different from what we are now. Darker skin, certainly. Much more melanin to protect against higher UV radiation. Possibly different eye structures, as we discussed. Better heat tolerance. More efficient sweating, or alternative cooling mechanisms. Our psychology might be different too. Growing up with unpredictable light cycles, with the need to constantly adapt, with the knowledge that your environment is unstable, how does that shape your worldview, your culture, your relationship with planning and permanence? Perhaps it creates cultures that value flexibility over stability, adaptability over tradition, innovation over conservation. Perhaps it creates societies that are nomadic by nature, that see movement as natural and settlement as strange. Perhaps it makes people more aware of cosmic forces, more likely to study astronomy seriously, because understanding the stars isn't just intellectual curiosity, it's survival. Or perhaps it creates the opposite, a desperate desire for stability, for control, for anything that can be predicted and managed. Technology as a way to impose order on chaos. Architecture as a shield against the variable sky. Culture as a bulwark against the changing climate. We can't know. What we can observe is that life on Earth has adapted to every extreme environment we've found, from boiling hot springs to Antarctic ice, from the crushing pressure of the deep ocean to the thin air of high mountains, from the most abundant rainforests to the driest deserts. Life finds a way. Life is flexible. Life is creative. So in a world with two suns, life would adapt. It would find solutions we haven't imagined. It would create forms that seem impossible until you see them working. It would be different from Earth life, certainly. Strange to our eyes. Alien in its adaptations. But it would still be life. Still growing. Still reproducing. Still evolving. Still finding ways to thrive in whatever conditions the universe provides. The plants might be black instead of green. The animals might have slit pupils and radiator fins. The ecology might be based in oceans rather than on land. The intelligent species might be aquatic or have completely different activity patterns than we do, or possess senses we don't have. But they'd still be alive, still competing and cooperating, still eating and being eaten, still dying and reproducing. The fundamental patterns of life, the ones shaped by chemistry and physics and evolution, those would remain the same. Only the specifics would change. And perhaps that's the most important lesson here. Life isn't fragile because it requires specific conditions. Life is robust because it can adapt to varying conditions. The parameters might shift. More light, more heat, more complexity. But life adjusts. Evolution is patient. Given time, given variability, given the raw materials of chemistry and energy, life finds its way. A world with two suns wouldn't be lifeless, it would just be different. And that difference, that strangeness, that alien quality, it would be beautiful in its own right. Not better than Earth life, not worse, just different. Just another expression of the endless creativity of evolution working with whatever the universe provides. So, if somewhere out there, orbiting binary stars, there are forests of black leaves and creatures with slit pupils and oceanic civilizations that have never known the stability of one sun, they're as valid as we are, as alive as we are, as much a part of this universe's story as we are. They're just writing a different chapter, one with twin suns instead of one with doubled shadows and complex light, one with challenges we've never faced and solutions we've never needed. And somehow, that makes the universe richer, not just in one way of being alive, but in many. Not just life as we know it, but life as it might be. Not just green leaves under yellow sun, but black leaves under orange and red twins, and every other variation the laws of physics allow. Life finds a way, always, under any sun or any two suns or however many suns the universe decides to provide. That's not just resilience, that's poetry. We have explored what a world with two suns could offer: complexity, abundance, strangeness, beauty. But let's be honest about what we'd lose, because in gaining something new, we inevitably give up something else. And there are aspects of our single-sun world that are so fundamental to our experience, we barely notice them until we imagine them gone. Let's start with the night sky, the real night sky, the one we have now when our sun sets and darkness falls and the stars emerge. Under two suns, especially in configurations where both are relatively close and bright, true darkness becomes rare or non-existent. During those nights when both suns are down, yes, you'd see stars, but those nights are precious few. Most of the time, at least one sun is above the horizon, washing out the fainter lights. The Milky Way, that river of light that our ancestors knew intimately, becomes difficult or impossible to see. The constellations that guided sailors and inspired myths fade into the background glare. Think about what humanity has lost here on Earth just from our own light pollution. People living in cities rarely see more than a handful of bright stars. The night sky that inspired ancient astronomers, that made them wonder about the cosmos, that sparked questions about our place in the universe. Most modern humans never experience it. Now, imagine that, on a planetary scale. Imagine an entire species growing up with only glimpses of the stars. Rare moments of true darkness treasured and celebrated because they're so unusual. Astronomy would develop differently, or maybe not develop at all in the way we know it. The science that taught us we orbit the sun, that discovered other planets, that revealed galaxies beyond our own. It all started with looking up at a dark sky and noticing patterns. If the sky is rarely dark, if stars are washed out by constant sunlight, would anyone bother to study them? Would we know there's a universe beyond our binary system? Perhaps astronomy would only emerge as a science during those rare dark periods. Perhaps the first astronomers would be like storm chasers, waiting for the specific orbital conditions that bring true darkness, setting up their instruments in that brief window, making observations before the light returns. Or perhaps astronomy would develop through different means, studying the suns themselves, learning about stellar dynamics from the visible binary system, then gradually realizing that the faint points of light visible during rare nights are other suns, impossibly far away. But we'd lose something profound if we couldn't see the stars clearly. That sense of being part of something vast, that humbling recognition that our world is just one of countless others. The overview effect, the cosmic perspective, it's harder to achieve when the cosmos is hidden behind the glare of your own suns. We'd also lose the simple beauty of a starlit night, the experience of lying on your back in a meadow, looking up at thousands of pinpricks of light, picking out constellations, watching for meteors, the quiet contemplation that comes with darkness, the feeling of being small but connected to something infinite. These are experiences that have shaped human culture for as long as we've been human. Poetry about stars, myths about constellations, navigation by stellar positions, romance under starlight, all of it would be different or absent. The moon, assuming we still have a moon in this scenario, would be diminished too. Right now, moonlight is the second brightest natural light source after the sun. A full moon can cast shadows, illuminate a path, provide just enough light to navigate by. It's romantic, mysterious, the subject of countless songs and stories. But in a system with two suns, moonlight would often compete with sunlight. During periods when one or both suns are above the horizon, the moon is just another object in the sky, washed out, unremarkable. Only during true night would it reclaim its status as a significant light source, and if true night is rare, the moon's cultural importance would be diminished. Fewer moon-related myths, less lunar calendar keeping, no werewolves probably, because the full moon wouldn't be special enough to inspire that kind of mythology. There's something about the cycle of light and dark that's fundamental to how we experience time. Day and night, the rhythm of waking and sleeping, the sense that each day is a complete unit, beginning with sunrise and ending with sunset. This rhythm has shaped human culture since before we were humans. It's shaped all of mammalian biology. It's one of the most reliable patterns in nature. But with two suns, this rhythm breaks down. Day and night stop being predictable cycles tied to Earth's rotation. Sometimes you have day for 3 rotations in a row. Sometimes you have variable intensity light with no clear beginning or end. The sense of a day as a meaningful unit of time weakens. And with it goes some of our intuitive understanding of duration, of routine, of the passage of time. We'd lose the simplicity of a single reference point in the sky. Right now, if someone says the sun is in the east, you know exactly what they mean. Direction, time of day, all implied in a simple statement. But with two suns, which one? The orange dwarf or the red dwarf? The primary or the secondary? Are they both in the east or one east and one west? Language would need to accommodate this complexity, and something would be lost in that accommodation. The elegance of simplicity, the ease of shared understanding. Seasons as we know them would be gone. Spring, summer, autumn, winter. These aren't just temperature changes. They're cultural frameworks. They're emotional associations. Spring means renewal, new growth, hope. Summer means abundance, warmth, ease. Autumn means harvest, preparation, change. Winter means rest, introspection, endurance. These metaphors are baked into our language, our literature, our way of understanding life cycles. In a binary system, especially with a distant companion star, seasons would be much longer and less predictable. Or, in a close binary system, they'd be tied to complex orbital mechanics that don't map neatly onto our emotional associations. You'd lose the annual cycle that synchronizes so much of human activity. Holidays tied to seasons would need to be reconceived. Agricultural traditions would be different. The sense of the year as a meaningful cycle would weaken. We'd lose the comfort of predictability. Right now, barring catastrophic events, we know the sun will rise tomorrow. It will set tomorrow evening. This rhythm has continued for billions of years and will continue for billions more. It's one of the few things in life that's genuinely reliable. That predictability is psychologically important. It provides structure, it allows planning, it gives us a foundation of stability in an otherwise uncertain existence. But in some binary configurations, predictability is harder to come by. The light changes, the heat fluctuates. What's comfortable today might be harsh tomorrow. That fundamental uncertainty would shape psychology, culture, the way people think about the future. It might make societies more flexible and adaptive, but it would also remove one of our deep sources of comfort, the knowledge that the sky operates according to rules we can count on. There's a particular quality to late afternoon light that photographers call golden hour, that warm, soft glow that happens when the sun is low on the horizon. It's caused by light passing through more atmosphere, which scatters blue wavelengths and leaves the reds and oranges. Artists throughout history have tried to capture this light. It appears in paintings, photographs, poems. It's associated with nostalgia, with endings, with the bittersweet beauty of things that don't last. With two suns, golden hour becomes complicated. Do you get it with both suns, with one? Does it happen when they're both low, or just one? The specificity of the experience would be lost. That particular quality of light that everyone recognizes, that has the same emotional resonance across cultures, it would be replaced by a variety of lighting conditions, some similar, some different, none quite the same. We'd lose the singular poetic metaphor of the sun. In our language, the sun means constancy, warmth, life, hope. My love is like the sun means something clear and powerful. But what does it mean when there are two suns? Do you compare someone to both? To one? Which one? The metaphor fragments. Language adapts, certainly, but something is lost when the central symbol becomes plural. And there's this, the simple experience of being alone with your thoughts under a quiet sun, walking in the morning when the light is fresh and the world is waking, sitting in the evening as the sun sets and day transitions to night. These are moments of transition, of reflection, of peace. They're possible because there's a rhythm, a predictability, a sense that this moment in the cycle has a particular quality. With two suns and unpredictable light patterns, these moments become harder to find. There's no longer a time of day that reliably feels contemplative or energizing or peaceful. The light is what it is, depending on complex orbital mechanics, and your experience is subject to that. You lose some agency over your own emotional landscape because the external environment is less predictable. None of this means life under two suns would be worse necessarily, just different. But difference involves trade-offs, and it's worth acknowledging what we'd be trading away. We'd be trading the dark, star-filled nights that inspired millennia of wonder, the simple poetry of one sun rising and setting, the predictable seasons that structure our years, the reliable rhythm of day and night that structures our days, the singular metaphors that make our language rich with meaning, the specific quality of golden hour light, the comfort of cosmic predictability. In exchange, we'd get complexity, variety, the beauty of twin shadows and doubled light, the challenge of adaptation, the richness of a culture shaped by multiple celestial partners instead of one. But it's not clear that this is an even trade. Some things about our single sun system are not just familiar, they're deeply connected to what makes human experience meaningful, the rhythm of light and dark, the reliability of celestial patterns, the ability to see beyond our immediate environment to the vast universe beyond. Perhaps the species that evolves under two suns doesn't miss these things because they never had them. To them, variable light is normal. Rare darkness is special. Twin shadows are just how shadows work. They don't feel like they're missing anything because they don't know what they don't have. But we know. We know what a dark, star-filled sky looks like. We know the comfort of predictable sunrise. We know the metaphorical weight of the sun in our language and thought. And imagining its loss helps us appreciate its presence. This is the purpose of thought experiments, isn't it? Not to make us wish we were somewhere else, but to help us see where we are more clearly. By imagining two suns, we learn to notice our one sun. By imagining constant light, we learn to value darkness. By imagining complexity, we appreciate simplicity. We have one sun. It rises and sets predictably. It gives us clear days and dark nights. It allows us to see the stars and understand our place in the universe. It provides a single, reliable reference point for time and direction and metaphor. And having explored what we might gain with a second sun, we can now recognize what a gift it is to have just one. Not because two suns would be bad, not because we couldn't adapt, but because there's a particular kind of beauty in simplicity, in reliability, in the gentle rhythm of one sunrise, one sunset, one clear distinction between day and night. This is what we'd lose, the elegance of singularity, the poetry of one, the comfort of predictability, the dark sky full of stars. These things are worth noticing, worth appreciating, worth being grateful for while we have them. Because in 5 billion years we'll lose them anyway when our sun begins to die. But for now, for this moment, for all the moments of our lives and our children's lives and countless generations to come, we have something precious. One sun, faithful and constant, simple and singular. And that perhaps is exactly what we need. But let's not dwell only on loss, because while two suns would take away certain things we cherish, they'd also offer gifts we can barely imagine. Experiences that don't exist in our single-sun world. Beauty that's impossible here but ordinary there. Perspectives that would shape consciousness in entirely new directions. Let's start with the most obvious, the sheer visual spectacle. Imagine stepping outside on a morning when both suns are rising, not one golden disk climbing over the horizon, but two, one perhaps larger and warmer in colour, the other smaller and cooler. They don't rise at the same point. They're separated, following their own paths, but both ascending together. The sky doesn't just brighten, it ignites. Colours you've never seen in a dawn, combinations of light that our single sun can't produce. The shadows around you are complex, doubled, creating patterns of light and dark that shift as both suns climb higher. This isn't something you'd see once in a lifetime. This would be your regular experience, your normal, and familiarity doesn't diminish beauty. Ask anyone who lives near mountains or oceans. They still notice, they still appreciate. Having two suns means having twice the opportunities for stunning sunrises and sunsets, and variations on those events that we can't experience. Think about what photographers could do with this, the play of light and shadow when two sources illuminate a subject from different angles, the colours mixing in the sky during sunset, not just the golds and pinks we know, but new combinations as different wavelengths from different stars interact with atmospheric particles. Portrait photography where your subject casts two shadows, each shadow different in colour temperature, creating depth and dimension impossible with one light source. Art in general would be transformed. Painters wouldn't just have golden hour, They'd have multiple distinct lighting conditions throughout the day, different qualities of light to capture, each one unique. The Impressionists were obsessed with how light changed through the day, painting the same scene at different times to capture those variations. Imagine what they could do with twice as many variables. Architecture would become an art form in new ways. Buildings could be designed to work with dual light sources, windows positioned to catch one sun in morning and another in evening, courtyards that create intricate shadow patterns when both suns are overhead, structures that look completely different depending on which sun is illuminating them. The Taj Mahal is famous for how it changes appearance throughout the day as the sun moves. Now imagine that times 2, with twice the transformation. And then there's the simple pleasure of variety. Right now, we have one type of daylight. It varies with weather, with time of year, with atmospheric conditions, but fundamentally it's light from one sun filtered through our atmosphere. With 2 suns, especially if they're different spectral types, you'd have genuinely different kinds of daylight. The warm, golden light when the orange dwarf is up alone. The cooler, almost silver light when the red dwarf is solo. The intense, complex light when both are overhead. And all the gradations in between. Your world wouldn't just have one look, it would have many looks. And which one you're experiencing would depend on orbital mechanics and time of day and the dance of the stars. This variety would make life more interesting, not just visually, but emotionally. Different light affects mood. There's a reason seasonal affective disorder exists, why winter darkness can be depressing. But with 2 suns and variable light patterns, you'd have natural variety built into your environment. Perhaps this would create more emotional resilience, more psychological flexibility, a population that's less tied to specific conditions for well-being. The complexity of the sky would inspire a different kind of curiosity. Right now, understanding our solar system requires careful observation and abstract thinking. The planets look like bright stars unless you use a telescope. The sun's motion across the sky can be explained by Earth's rotation and orbit, but it's not intuitively obvious. You need to do some mental work to understand what's happening. But with 2 suns visibly orbiting each other, orbital mechanics becomes intuitive. You can see the dance. You can watch one sun move relative to the other, watch them circle their common center of mass. It's a real-time demonstration of gravitational physics, played out in your sky every day. This might make populations naturally more scientifically literate. When the evidence of complex physics is that obvious, you can't help but wonder about it, try to understand it, develop theories to explain it. Science education would be fundamentally different. Teachers wouldn't need to use analogies or models to explain how binary systems work. They could just point at the sky. See how the smaller sun is moving faster in its orbit? That's because it's farther from the center of mass. Let's calculate why. Abstract concepts become concrete observations. Theory becomes reality you can watch. This might accelerate scientific development overall. When the universe demonstrates its complexity so visibly, when you can't look at the sky without seeing questions that need answers, curiosity becomes unavoidable. Perhaps binary system civilizations developed physics earlier than we did, mathematics earlier, technology earlier, simply because their environment poses more obvious questions. Navigation would be harder, as we discussed, but also richer. Right now we have one sun, the stars, and the magnetic field. In a binary system, you'd have 2 suns whose relative positions are constantly changing, creating a much more complex navigation challenge. But complexity breeds sophistication. Perhaps binary system navigators develop more advanced mathematical systems, better spatial reasoning, more elegant solutions to 3-dimensional movement problems. The mythology would be extraordinarily rich. Two suns means two deities, or two aspects of one deity, or two characters in a cosmic drama. The stories you could tell, the meaning you could make, partners, rivals, parent and child, creator and destroyer. The variations are endless, and each culture would find its own interpretation. Think about how monotheistic religions might develop differently with two suns. Does the divine create one sun or both? Are they equal, or is one primary? The theological questions would be fascinating. Duality as a fundamental aspect of creation, the concept of partnership or balance built into the structure of the universe. This might create religions that are less hierarchical, more focused on relationship and balance than on singular authority. Or polytheistic religions. Now you have a built-in binary at the center of your pantheon. Two sun gods, clearly visible, clearly real, in the sense that the suns themselves are real, and their relationship explains the patterns you observe. When the suns are close together in the sky, the gods are harmonious. When they're separated, there's tension. When one eclipses the other, there's conflict or dominance or sacrifice, depending on your interpretation. The calendar would be a work of mathematical and astronomical art. You'd need to track multiple cycles: Earth's rotation, Earth's orbit around the binary pair, the Sun's orbit around each other, possibly the changing distance between Earth and the binary pair if the orbit is elliptical. Creating a calendar that accounts for all these variables would be a significant achievement, and the civilization that managed it would be rightfully proud. And perhaps this would create a culture that's more aware of time's complexity, that understands that duration isn't simple, that cycles nest within cycles, that patterns emerge at multiple scales. This kind of temporal awareness could be valuable philosophically, making people more comfortable with complexity, more patient with long-term processes, more able to see patterns in what appears chaotic. The social structures might be influenced by duality. If your universe is fundamentally binary, two suns instead of one, perhaps your social systems reflect that. Partnership as the fundamental unit rather than the individual. Dualistic philosophy is where balance between opposites is the goal. Political systems based on co-leadership, shared authority, checks and balances built in at every level. This isn't deterministic. Culture is shaped by many factors, not just astronomy, but the symbolism would be there. When your sky contains a visible partnership that sustains all life, when cooperation between two entities is literally what makes your world possible, that symbolism would certainly influence how you think about relationships, governance, ethics. The experience of shadow would be unlike anything we know. Right now, shadow is simple. Light blocked by an object creates darkness on the far side. But with two suns, you get three types of shadow. The shadow cast by sun, A, where sun B's light can't quite fill it in. The shadow cast by sun B, where sun A's light doesn't reach. And the deep shadow where neither sun reaches, the overlap of both shadows, the darkest place possible in doubled light. Artists would play with this. Children would play with this. The game of shadows becomes more complex, more interesting, more full of possibilities. You could create shadow plays with dual projections, telling stories with overlapping shadows that create patterns impossible in single-source lighting. And the rare darkness, when it comes, would be more precious than any darkness we experience. Because it's rare, because it's temporary, because you know it will give way to light again soon. Those dark hours would be treasured. Festivals during darkness, special activities, sacred times. The darkness we take for granted would be a gift to them, an unusual condition worth celebrating. There would be energy abundance, at least potentially. Two suns means more solar radiation reaching your planet. If you can manage the heat, and that's a big if, You have access to more energy than we do. Solar power becomes even more viable. Photosynthesis, if plants adapt properly, could be more productive. The fundamental energy budget of your planet is higher, which allows for more complex ecosystems, larger populations, more activity. This might seem like a minor point, but energy is fundamental to civilization. More available energy means more possibilities, more margin for error, more room for innovation and experimentation. A civilization with abundant solar energy from two sources might develop differently, might be more ambitious, might achieve more simply because they have more energy to work with. The psychological impact of living under doubled light might be positive in ways we don't expect. More light generally correlates with better mood. There's a reason bright sunny days feel good, while overcast days can feel gloomy. If you're getting more light more often, perhaps that creates a population that's generally more energetic, more optimistic, more active. The downside is less rest and recovery from constant stimulation, but the upside might be a culture that simply operates at a higher energy level. And there's this, the sheer wonder of it. Growing up in a world where the sky contains two suns, where the astronomical situation is visibly complex, where you can see cosmic machinery at work, that would inspire a sense of living in something special. Not special because you're chosen or central, but special because your experience is distinct, your view of the universe is unique. We live under one sun, and it's easy to think that's normal, that it's the default, that every world must be like this. But seeing two suns would remind you constantly, the universe has variety. There are many ways to be a planet. Your experience is one among many possibilities. That awareness, that cosmic perspective built into your daily experience might make for a wiser, more humble, more curious civilization. Perhaps most importantly, two suns would give you twice the appreciation. Right now, we take the sun for granted. It's always there, always reliable, always doing its job. We rarely think about it until we do thought experiments like this. But with two suns, the complexity is unavoidable. You can't take them for granted because they're always doing something different, always in a new configuration, always presenting a new aspect. This constant variation might create a culture of appreciation, not taking things for granted because things are always changing, noticing beauty because beauty comes in so many forms, being attentive to the sky because the sky is always worth watching. We'd gain wonder, we'd gain variety, we'd gain complexity that inspires curiosity and understanding. We'd gain symbols and meanings we don't currently have. We'd gain appreciation through constant change. These aren't small things. They're not just compensation for what we'd lose. They're genuine gifts, real advantages, actual improvements in some dimensions, even as other dimensions become more challenging. And two suns wouldn't make life better or worse, just different. But the differences would include genuine beauty, real wonder, and experiences impossible in our simpler single-sun world. And perhaps that's worth something. Perhaps that's worth a great deal. Perhaps, from a certain perspective, we're the ones missing out. We've imagined what life might be like under two suns, explored the beauty and challenges, the losses and gains. But now, let's address the practical question that underlies all of this. Could we actually survive? Not just in theory, not just with infinite adaptation time, but realistically, could a planet like Earth with a life like ours exist and thrive in a binary star system? The answer, somewhat surprisingly, is yes, probably in the right configuration. Let's talk about the habitable zone first, because this is where everything starts. The habitable zone is the region around a star where temperature allows liquid water to exist on a planet's surface. Too close, and water boils away. Too far, and it freezes solid. Earth sits comfortably in the middle of our sun's habitable zone, which is why we have oceans and rivers and rain, all that liquid water that makes life as we know it possible. In a binary star system, the habitable zone is more complicated. It's not a sphere around one point anymore. It's a ring or a more complex three-dimensional region around both stars, or around just one, if the companion is far enough away. But it exists. Calculations show that stable habitable zones are possible in many binary configurations. For a distant companion scenario, our first and gentlest configuration, the habitable zone is basically unchanged. If the second sun is far enough out, say hundreds of astronomical units away, Earth can orbit the primary sun just as it does now. The companion's influence is minimal. We stay in the habitable zone, receive most of our heat from the primary sun, and the companion is just a bright star in the night sky that adds a little extra warmth. This is the most survivable scenario because it's closest to what we already have. For a circumbinary orbit, the Tatooine scenario, things get trickier but still possible. The habitable zone forms a ring around both stars farther out than if the stars were separate because you're receiving heat from two sources. NASA scientists have actually calculated this. For a system like Kepler-16, two stars orbiting each other every 41 days, the habitable zone starts at about 0.7 astronomical units from the binary pair. The planet Kepler, 16b, is real, and it orbits in this region, though it's a gas giant, so not itself habitable. But a rocky planet could exist in that zone. It would receive warmth from both stars, with the amount varying depending on the star's positions relative to Earth. Sometimes you'd get more heat, sometimes less, but averaged over time, it could be right in the Goldilocks range. Not too hot, not too cold. Just right for liquid water, for life, for everything that makes a planet habitable. The catch is stability. A circumbinary orbit needs to be far enough from the binary pair that the planet's orbit doesn't get disrupted by the complex gravitational dynamics. Too close, and the gravitational tugs from each star, constantly changing as they orbit each other, would eventually destabilize the planet's orbit. You need to be at least 2 to 3 times farther from the binary pair than the stars are from each other. This creates a minimum distance for stable orbits, which in turn means there's a minimum amount of stellar luminosity. You need to keep that distant planet warm enough. So yes, it's possible, but it requires specific conditions. 2 stars that are not too different in mass. Large imbalances create more complicated dynamics. An orbital separation that's not too large and not too small. A planet that orbits far enough out to be stable but close enough to stay warm. It's a narrower range of possibilities than our current situation, but it's not impossibly narrow. The universe is large. It probably contains millions of planets in stable circumbinary orbits within habitable zones. Now, the Figure 8 scenario, our most chaotic option, is much less likely to be stable long-term. The mathematics of three-body problems tell us that most such configurations eventually end badly. But eventually, in astronomical terms, might mean millions of years, which is plenty of time for life to exist, even for intelligent life to emerge. So while we wouldn't expect to find many planets in Figure 8 orbits, if we did find one, it might support life for a geologically significant period before things destabilize. Let's rank our scenarios by survivability, from most to least. Likely to support human-like life. First place, distant companion. This is barely different from what we have now. Earth orbits one sun normally, and there happens to be a second sun far away. The changes are subtle: long-term climate cycles, an extra bright star in the sky, some cultural and mythological differences. But fundamentally, this is an Earth-like planet with Earth-like conditions. Humans could live here without any biological adaptations. We just need to understand the long-term climate patterns and plan accordingly. Survivability, excellent. Second place, circumbinary orbit, Tatooine scenario. This is more challenging, but definitely possible. The heat fluctuations as the stars orbit each other would create climate variability, but not beyond what life can handle. The complex light patterns would affect circadian rhythms and agriculture, but adaptations exist: artificial lighting, underground farming, flexible sleep schedules. The main challenges are engineering and cultural rather than biological. Humans could live here with current technology, though it would be uncomfortable without significant infrastructure. Survivability, good, with preparation. Third place, Figure 8, orbit. This is the least survivable scenario. The extreme temperature swings, the unpredictable climate, the constant need to migrate or shelter. These make complex life difficult. Not impossible, but difficult. Humans could potentially survive here with a very advanced technology: underground cities, climate-controlled environments, the ability to move or hibernate through extreme periods, but it would be survival, not thriving. Most of your energy would go toward coping with the environment rather than building civilization. Survivability, poor without advanced technology, possible with it. The key insight is that binary star systems aren't inherently hostile to life, they're just different, and life is remarkably adaptable. Given the right conditions, stable orbit, habitable zone temperatures, liquid water, life would emerge and evolve just as it did on Earth. It would just evolve different solutions to different problems. Consider the real examples we've found: Kepler 16b, Kepler 34b, Kepler 35b, Kepler 38b, Kepler 47c. All confirmed planets orbiting binary stars. Granted, most of these are gas giants, not rocky worlds, but their existence proves that planets can form in binary systems, can achieve stable orbits, can persist for the billions of years needed for planetary systems to mature. Kepler 47c is particularly interesting because it's in the habitable zone of its binary system. It's probably too large to be rocky, likely a Neptune-sized gas giant, but if it has moons, those moons could potentially support life. A moon orbiting a gas giant that orbits binary stars. 3 levels of orbital complexity, and still potentially habitable. The universe is more flexible than we might assume. The discovery of these circumbinary planets has changed how astronomers think about binary systems. Before Kepler, there was genuine uncertainty about whether planets could even form in such environments. The gravitational dynamics seemed too chaotic, but nature doesn't care about our assumptions. Planets form where conditions allow, even in binary systems. And if they form, if they can maintain stable orbits, then life, stubborn, creative, adaptable life, might find a way. From an engineering perspective, if humans wanted to colonize a binary star system, we could. We'd face challenges, certainly. The variable starlight would require flexible solar panel systems. The complex light cycles would need artificial management for crops. Architecture would need to handle thermal cycling. Social structures would need to accommodate unusual sleep and activity patterns. But these are solvable problems. We've built research stations in Antarctica, where conditions are far outside human comfort zones. We've lived in space stations with completely artificial environments. We've created underground facilities, sealed habitats, closed-loop life support systems. The technology exists or is within reach. A binary system colony would be more challenging than a single sun colony, but not impossibly so. In fact, some binary configurations might be preferable to some single-star scenarios. A binary system with a stable habitable zone gives you redundancy. If something happens to one star, unlikely on human timescales but theoretically possible, you still have another. You have twice the resources if you're harvesting stellar material for fusion reactors. You have a more complex system to study and learn from. The atmospheric requirements wouldn't change. Life still needs the same basic chemistry: carbon, hydrogen, oxygen, nitrogen. Water is still the universal solvent. The building blocks of biology aren't dependent on having one sun versus two. Only the conditions need to be right: temperature, pressure, chemical availability. And those conditions can exist in binary systems just as they do in single-star systems. The real question isn't whether survival is possible. It clearly is, in the right circumstances, but whether it's likely that we'll find life in binary systems when we get better at detecting biosignatures on exoplanets. And the answer is probably yes. Not definitely, because we don't know how common life is in general. But if life arises readily when conditions are suitable, and if suitable conditions can exist in binary systems, then some fraction of the universe's life probably exists under two suns. Perhaps a significant fraction. Remember, binary systems are more common than single stars. If they're not dramatically less hospitable to life than single-star systems, then most of the life in the universe might be experiencing what we've been imagining. Most living beings might look up at a sky with two suns and think that's normal. We might be the unusual ones with our solitary star. This is speculative, of course. We don't have confirmed examples of life beyond Earth yet, in any type of system. But the possibilities are there. The physics allows it. The chemistry supports it. The real-world examples of stable circumbinary planets prove that the orbital mechanics work out. So could we survive in a binary star system? Yes, in most configurations we've discussed. Could life evolve there naturally? Yes, almost certainly, given enough time and the right conditions. Could intelligent civilizations arise? Yes, with the same probability as in single-star systems, whatever that probability turns out to be. Binary systems aren't death traps. They're not hostile cosmic environments where life withers and dies. They're just different, more complex certainly, more challenging in some ways, but also offering unique opportunities, unique beauty, unique experiences that single-star systems can't provide. If you were born on a planet orbiting binary stars, you wouldn't think of it as a survival challenge. You'd think of it as normal, as home. The two suns in your sky would be as natural to you as our single sun is to us. You'd have adapted, biologically, technologically, culturally, to thrive in those conditions. And you might look at single-star systems and think they seem boring, simple, missing something. The universe contains multitudes, single stars and binary stars, triple systems and more, planets in all sorts of configurations, and wherever conditions allow, life likely finds a way to exist, to adapt, to thrive in whatever environment it's born into. Could we survive under two suns? Yes. Could we thrive? In the right circumstances, also yes. Would we want to? That depends on your tolerance for complexity, your appreciation for variety, and your willingness to adapt to conditions different from what we evolved for. But the option is there. The universe provides it. Binary star systems with habitable zones exist, waiting for life to discover them, evolve in them, perhaps eventually look up at their twin suns and wonder, as we're wondering now, what it would be like to have just one. And somewhere, someday, Perhaps a being evolved under binary stars will imagine what we have. One sun, simple and singular, reliable and predictable. They might find that comforting, or they might find it limiting, or they might, like us looking at them, simply find it fascinating. Another way of being, another possibility, another expression of the endless creativity of the universe in arranging matter and energy into forms that can wonder about themselves. Survival is possible, life is adaptable, the universe is large. And two suns, it turns out, are not an ending, they're just another beginning. So we've journeyed through multiple scenarios, imagined forests of black leaves and skies with double shadows, explored circumbinary orbits and figure-8 trajectories, contemplated what we'd lose and what we'd gain. We've asked whether we could survive and found that yes, in the right circumstances, we could. But now let's step back and ask the bigger question. What's the point of all this imagining? What does this thought experiment actually teach us? The first lesson, I think, is about appreciating simplicity. We have one sun, just one. It rises in the east and sets in the west with absolute reliability. It provides predictable light on a predictable schedule. Our seasons follow a regular pattern. Day and night alternate with a rhythm so consistent we literally set our clocks by it. This simplicity is a gift we rarely acknowledge because it's so fundamental to our experience we don't even see it as a choice the universe made. But it was a choice, or at least a possibility among many. The universe could have placed Earth in a binary system. We could have been born into complexity, into variable light and unpredictable patterns and doubled shadows. We weren't. We got the simple version. And having imagined the complex version, we can now see our simple version for what it is. Not inevitable, not the only way, but a particular arrangement that happens to be elegant and manageable and kind to life. There's something to be said for simplicity, not because complexity is bad. We've seen that binary systems have their own beauty, their own gifts, but because simplicity allows you to focus on other things. When your astronomical environment is straightforward, you don't need to spend as much energy managing it. You can devote your attention to art, science, philosophy, relationships, all the things that make life rich beyond mere survival. Our single sun is like living in a house with good bones and solid infrastructure. Everything just works. The heating is reliable. The lights come on when you flip the switch. You don't think about it much, which frees you to think about other things. Binary systems are like living in a quirky old house with character and charm, but also complex maintenance requirements. Both are valid ways to live. But there's something to be said for simplicity. The second lesson is about the flexibility of life. We've explored scenarios where life would need to be fundamentally different from what we know. Plants that are black instead of green, animals with heat radiator fins, civilizations that migrate constantly or live underground, and in every case, we found that it's possible. Difficult, perhaps, requiring adaptations we don't possess, but possible. This tells us something profound about biology. It's not rigid. The parameters can shift, more light, different light, variable conditions, and life adjusts. Evolution is patient and creative. Given time, given variation, given the basic building blocks of chemistry, life finds solutions. This matters for our understanding of life beyond Earth. We often think about habitable zones as narrow bands where conditions are just right, and they are, for life as we know it. But life as we don't know it might thrive in places we'd consider hostile. A planet orbiting binary stars might seem challenging to us, but to life that evolved there, it's home. It's normal. It's what just right means in that context. This expands the search space for extraterrestrial life enormously. Binary systems aren't just curiosities, they're potential homes for biology, for consciousness, for civilizations. More than half the star systems in our galaxy are binary or multiple. If even a fraction of those can support life, then most of the life in the universe might be experiencing conditions very different from ours. And that's exciting. It means the universe is more varied, more creative, more full of possibilities than we might assume from our single data point. It means that when we finally detect life beyond Earth, if we detect it, it might be stranger than we imagined, not because it's exotic by universal standards, but because we assumed our experience was typical, and it might not be. The third lesson is about the nature of normal. Throughout this journey, we've encountered the same pattern. What seems strange to us would seem normal to anyone born into it. 2 suns in the sky, variable darkness, complex shadows, unpredictable seasons. These would just be how things are. Children growing up under binary stars wouldn't think of their world as unusual any more than we think of ours as unusual. This is a lesson in perspective. Normal isn't an absolute category. It's what you're accustomed to, what you evolved for, what your culture is built around. And recognizing this helps us understand that our way of experiencing reality isn't the only valid way. This applies beyond astronomy. It's true of cultures, of languages, of social structures, of ways of thinking. What seems natural and obvious to us might seem strange to others, and vice versa. And neither perspective is more correct. They're just different viewpoints from different positions. Imagining life under 2 suns doesn't just teach us about binary systems. It teaches us humility. It reminds us that our experience, however universal it feels from inside it, is particular, specific to our circumstances. Other experiences are equally valid, equally real, equally normal to those living them. The fourth lesson is about gratitude through contrast. We started this journey by imagining abundance, 2 suns instead of 1, more light, more energy, more complexity. And we found that abundance comes with costs, trade-offs, challenges that single-sun systems don't face. By the end, having explored what we'd gain and what we'd lose, we're left with a deeper appreciation for what we actually have. This is the purpose of thought experiments like this. Not to make us wish we were elsewhere, but to help us see where we are more clearly. By imagining 2 suns, we learn to notice our 1 sun. By imagining constant light, we appreciate darkness. By imagining complexity, we value simplicity. Gratitude through contrast. It's a powerful tool, and it works because imagining loss or change makes the familiar strange, makes the overlooked visible, makes the taken for granted precious. Tomorrow when you see sunlight, and you will, because unlike in our thought experiment where the sun disappeared, this sun is staying put, maybe you'll notice it differently. Not as an automatic background condition, but as a specific feature of your world. 1 sun, rising predictably, setting reliably, providing light and warmth according to patterns that have held steady for billions of years. That's not nothing, that's something to appreciate. The 5th lesson is about the limits of imagination. We've done our best to imagine what life under 2 suns would be like. We've thought about the biology, the physics, the culture, the experience. But here's the thing, we can only imagine from within our own framework. We're single-sun creatures thinking about a binary sun world. We're limited by our experience, our biology, our cultural assumptions. Someone who actually evolved under 2 suns would experience it in ways we can't fully grasp. Just as someone who's never seen colour can't truly imagine what red looks like. We can't truly imagine what it feels like to have 2 suns as your normal. We can describe it. We can calculate it. We can create scenarios. But the subjective experience, the qualia, philosophers would call it, remains beyond our reach. This is a lesson in epistemic humility. There are limits to what we can know from the outside. We can study exoplanets, analyze their atmospheres, determine whether they're inhabitable zones. But until we actually visit, or until we make contact with life that evolved there, we won't really know what it's like. Our models are approximations. Our imaginings are educated guesses. And that's okay. The limitation doesn't invalidate the exercise. Imagining helps us think more clearly, ask better questions, prepare for possibilities. But it also reminds us that the universe is larger than our ability to imagine it, that reality will always exceed our models of it, that there's always more to discover. The sixth lesson, perhaps the most important one, is about the preciousness of this moment. We've imagined Earth with two suns, more energy, more complexity, more of everything. But we don't have two suns, we have one. And this particular arrangement of matter and energy, this specific configuration of star and planet and life, is temporary, unique in time and space. This exact moment, with you hearing these words under your single sun, will never occur again. In 5 billion years, our sun will die. Long before that, it will change enough that Earth becomes uninhabitable. Our time under this particular sun is finite, and recognizing that finitude makes the present more precious, not less. This isn't morbid, it's clarifying. The fact that something doesn't last forever doesn't diminish its value. If anything, it enhances it. The sunset is beautiful partly because it's temporary. The season is meaningful partly because it will change. And our time under our sun is precious partly because it's not eternal. So this thought experiment, this journey through the possibility of two suns, ultimately brings us back to the one sun we have, not with disappointment that it's only one, not with regret that we don't have the complexity of a binary system, but with appreciation for what is, for the simplicity, the predictability, the elegant sufficiency of our astronomical arrangement. We imagined more to appreciate what we have. We explored complexity to value simplicity. We contemplated change to recognize the gift of stability. And now, having taken this journey, we return. The thought experiment ends. The imagining concludes. We come back to reality, to Earth, to our single sun, to the actual conditions of our existence. And perhaps we see them a little differently now. Perhaps that single point of light in our sky seems less ordinary, more remarkable. Perhaps the rhythm of sunrise and sunset feels less automatic, more graceful. Perhaps the darkness of night, with its visible stars, seems more valuable. Or perhaps nothing has changed except our awareness. The sun is still the sun. The earth is still the earth. But we're paying attention now. We're noticing. We're appreciating what was always there, but easy to overlook in the dailiness of living. That's what this teaches us. Not facts about binary systems, though we've learned those too. Not details about orbital mechanics or photosynthesis or circadian rhythms, though those have been part of our journey. What this teaches us is how to see what we have, how to appreciate the particular constellation of circumstances that allows our existence, how to recognize that normal isn't neutral. It's a specific configuration that could have been otherwise, that is otherwise in other parts of the universe, but that here, for us, is exactly this. One sun, faithful and constant, simple and sufficient, rising tomorrow morning as it has every morning, as it will every morning for billions of mornings to come. That's our reality. And having imagined the alternative, having explored what two suns would mean, we can return to that reality with fresh eyes and deeper gratitude. The thought experiment is complete, the imagining is done, but the appreciation that can continue, that can grow, that can become a practice, a way of relating to your world, a habit of noticing what you might otherwise overlook. Two suns would be fascinating, complex, beautiful in their own way. But one sun is ours. One sun is what we have. One sun is sufficient. And that perhaps is the deepest lesson of all. We've spent all this time imagining, hypothesizing, exploring what might be. But here's something wonderful. We don't have to rely entirely on imagination anymore, because in the last 2 decades, astronomers have actually discovered planets orbiting binary stars. Real worlds, real Tatooines. Not science fiction, but science fact. And what we've learned from these discoveries is reshaping our understanding of what's possible in the universe. Let's start with Kepler 16b, because it's the first confirmed circumbinary planet, and it captured public imagination in a way few exoplanet discoveries have. Announced in 2011, it orbits 2 stars that orbit each other every 41 days. The planet itself takes about 229 days to complete one orbit around both stars. It's a gas giant, roughly Saturn's size, definitely not habitable by any definition we'd recognize. But it exists. It's stable, it's real. And its existence proved something important. Planets can form in binary systems. This might not sound revolutionary, but before Kepler 16b, there was genuine scientific debate about whether circumbinary planets were even possible. The gravitational dynamics seemed too chaotic. The protoplanetary disk, that swirling cloud of dust and gas where planets form, would be constantly disrupted by 2 stars tugging at it from different directions. How could material settle into stable orbits long enough to clump together into planets? The universe answered, it just does. Nature doesn't care about our models of what should be impossible. Given the right conditions, planets form around binary stars the same way they form around single stars. The process is messier, more complicated, but it works. Kepler 16b is the proof. Since then, we've found more. Kepler 34b, discovered in 2012, orbiting 2 Sun-like stars. Kepler 35b, also from 2012 in a similar configuration. Kepler 38b, Kepler 47b, Kepler 47c, Kepler 64b, Kepler 413b. The list keeps growing. Each discovery adds to our understanding of how these systems work, what configurations are stable, where planets tend to form. Kepler 47c is particularly intriguing because it's in the habitable zone of its binary system. Announced in 2012, it's the first circumbinary planet found in a region where liquid water could potentially exist on a planet's surface. Like Kepler 16b, it's a gas giant, too large to be rocky, probably more like Neptune than Earth. But the fact that it exists in the habitable zone proves that habitable zone circumbinary planets are possible. They're not theoretical anymore, they're actual. And if Kepler 47c has moons, which large gas giants often do, those moons could potentially be habitable. A rocky moon orbiting a gas giant which orbits binary stars, all positioned in the habitable zone. It's orbital mechanics all the way down, but it could work. Such a moon would experience complex cycles. The gas giant's day, the time to orbit the gas giant, the time the whole system takes to orbit the binary stars. Timekeeping would be a nightmare. But life might not care about timekeeping as much as we do. These discoveries are coming from the Kepler Space Telescope, which operated from 2009 to 2018. Kepler used the transit method, watching for the tiny dip in a star's brightness when a planet passes in front of it. This method works well for single stars, but is trickier for binary systems because you're looking for a planet-sized dip in the light from two stars that are themselves varying in brightness as they orbit each other. It's like trying to spot a firefly in front of a lighthouse that's already spinning. But Kepler managed it, finding these circumbinary worlds and proving they exist. The James Webb Space Telescope, launched in 2021, is now adding to our understanding. JWST can analyze the atmospheres of exoplanets, looking for chemical signatures that might indicate habitability or even life. It hasn't studied many circumbinary planets yet. They're harder targets and there's a lot of universe to look at. But in time, we might get atmospheric data from worlds orbiting binary stars. We might learn what their air is made of, whether they have water vapor, whether they show signs of biological activity. Imagine that. Imagine detecting biosignatures, oxygen, methane, other chemicals that in combination suggest life, in the atmosphere of a planet orbiting two suns. It would confirm something we've been imagining throughout this journey, that life doesn't just tolerate binary systems, it thrives in them, that doubled sunlight, far from being a barrier to biology, is just another condition to which life adapts. The European Space Agency's Plato mission, planned for launch in 2026, will specifically look for Earth-sized planets in habitable zones, including around binary stars. It's designed to find rocky worlds, not just gas giants. If circumbinary Earth analogues exist, and the statistics suggest they should, PLATO might find them. We might, within the next decade, discover a world where our thought experiment is reality. A rocky planet, the right size, the right temperature, orbiting two suns in a stable configuration where life could exist. What have we learned from these discoveries so far? First, that circumbinary planets tend to orbit relatively close to the stability limit, the minimum safe distance from the binary pair. This makes sense. Planets form from material in the protoplanetary disk, and the material is densest where gravity allows stable orbits. Form too close, and you get ejected or crash into one of the stars. Form too far, and there might not be enough material to build a planet, so planets form in that sweet spot just beyond the chaos zone. Second, that the orbital planes matter. Most circumbinary planets we've found orbit in roughly the same plane as the binary stars orbit each other. This alignment makes sense. The protoplanetary disk would naturally form in that plane. But it also means these planets experience regular eclipses, regular variations in light, predictable, if complex, patterns. Not the chaotic figure 8 scenario, but structured, calculable dynamics. Third, that gas giants seem to be common in these systems. This might be an observation bias. Kepler is better at finding large planets, or it might mean something about how planets form in binary systems. Perhaps the gravitational dynamics favor gas giant formation, or perhaps rocky planets form too but are harder to detect. We need more data, more observations, more discoveries. The search continues. Ground-based telescopes, space telescopes, new instruments and techniques. Every year we find more exoplanets. Some fraction of those will be circumbinary. Some fraction of those will be in habitable zones. Some fraction of those will be rocky. And some fraction of those might, just might, support life. The numbers are encouraging. We've discovered over 5,000 exoplanets total as of 2024. Of those, at least a dozen are confirmed circumbinary planets, and the number keeps growing. The detection methods improve, the technology advances. We're getting better at finding these worlds. And here's what's remarkable. Binary star systems are more common than single stars. If planets can form around binaries, and we now know they can, and if those planets can be habitable, and we know that's possible too, then a significant fraction of the galaxy's real estate is potentially open to life. Not just the roughly half of star systems that are single stars like ours, but also many of the binary and multiple star systems that make up the rest. This doesn't mean life is common. We still don't know how often life arises when conditions are suitable. That's one of the great unanswered questions, but it does mean that the number of potentially habitable environments is larger than we thought. The universe has more room for biology than a single star-centric view would suggest. Think about what this means for the search for extraterrestrial intelligence. SETI, the search for extraterrestrial intelligence, looks for radio signals from advanced civilizations. So far, we've found nothing, but we've only searched a tiny fraction of the sky, and we've focused primarily on single stars because we assumed those were more likely to host habitable planets. But if binary systems can host life, if civilizations can arise under two suns, then we've been overlooking half the potential sources of signals. Perhaps we should be listening to binary systems too. Perhaps the first message we receive will come from a species that grew up under doubled light, that never knew the simplicity of one sun, that thinks of day and night as complex variables, rather than simple cycles. What would they tell us? What would their perspective be? Would they find our single sun experience boring or peaceful or enviable or limiting? Would they understand our metaphors, our poetry about the sun as singular and central? Or would they have entirely different frameworks, different ways of thinking about light and time and cycles? We can't know until we find them, if we find them, but the possibility is there, and knowing the possibility is there changes how we think about the universe and our place in it. There's also this. Studying binary systems teaches us about stellar evolution. Two stars orbiting each other affect each other's development. They can exchange mass, influence each other's rotation, alter each other's lifespans. Binary systems are natural laboratories for understanding how stars work, how they interact, how they change over time. And planets in binary systems are natural laboratories for understanding planet formation, orbital dynamics, climate systems. Every circumbinary planet we study tells us something new, refines our models, challenges our assumptions, expands our knowledge of what's possible. This is the scientific value of these discoveries, not just, oh cool, planets around two stars, but genuine advancement in understanding how the universe works, how matter organizes itself, how gravity shapes systems, how life might emerge in diverse conditions. And perhaps someday, if we develop the technology for interstellar travel, binary systems might be destinations. Not because they're easier or better than single-star systems, but because they're there. Because they're different. Because human curiosity drives us to explore the various expressions of cosmic architecture. Imagine being part of the first expedition to a circumbinary planet, watching two suns rise in an alien sky, experiencing the complex interplay of dual shadows, studying an ecosystem that evolved under conditions unlike Earth's. It would be the ultimate validation of these thought experiments, seeing in reality what we've only imagined. For now, we watch from a distance. We detect these planets as tiny dips in starlight. We calculate their masses and orbits. We infer their conditions from mathematical models. But we're learning. And the more we learn, the more the universe reveals its creativity, its flexibility, its seemingly endless capacity for variation on basic themes. Binary stars are common. Planets can form around them. Habitable zones exist. Life might arise. Civilizations might develop. All of this is possible, and increasingly we're finding it's actual. The real Tatooines are out there. Not with moisture farms and twin sunsets that look exactly like the movie, but with their own unique configurations, their own beauty, their own possibilities. Worlds that would be strange to us and normal to any life that evolved there. Planets that prove the universe is more diverse, more interesting, more full of potential than a single sun world view would suggest. This is what we've learned from actually looking, from building telescopes and pointing them at the sky, and carefully, patiently gathering data. The universe answers our questions, but we have to ask them first. We have to look. We have to be curious enough to search and humble enough to be surprised by what we find. Binary planets are real. They exist. They're out there right now, orbiting their twin suns, following their complex paths, perhaps hosting life that looks up at doubled light and thinks this is simply what the universe looks like. And we're just beginning to understand them, just starting to catalogue them, just learning what's possible and what's common and what's rare. The search continues, the discoveries accumulate, and with each new circumbinary planet found, each new piece of data gathered, each new insight gained, our picture of the universe becomes richer, more complete, more full of wonder. We imagined what two suns might mean. Now we're discovering what they actually mean, out there in the real universe, in systems we can observe and study and gradually come to understand. The thought experiment becomes reality. The imagination meets observation, and the universe, as always, turns out to be more interesting than we expected. We've explored the physics, the biology, the survival scenarios, the real discoveries, but there's one more aspect we need to consider, and it might be the most important of all, the stories. Because humans are storytelling creatures. We make meaning through narrative. We understand our world through the tales we tell about it, and a world with two suns would tell very different stories than the ones we know. Let's imagine what culture would look like under twin stars. How would art, mythology, philosophy, and simple everyday storytelling be shaped by that doubled light in the sky? Start with the most basic human art form, visual representation. Painting, drawing, photography if the civilization advances that far. Here on Earth, artists work with single-source lighting. The sun, a lamp, a candle. One light creating one set of shadows, one quality of illumination. Artists spend years learning to master this, understanding how light falls on subjects, how shadows define form, how different times of day create different moods. But under two suns, you have multiple source lighting as the default. Every object casts two shadows, three shadows if you count the overlap. Colours mix in ways they don't hear, two different wavelengths of light hitting the same surface, creating hues that our single sun eyes have never seen. The entire visual vocabulary would be different. Painters wouldn't talk about the golden hour, but perhaps the confluence when both suns are at similar angles and their light combines most beautifully, or the separation when they're at opposite ends of the sky and everything is lit from two directions simultaneously, flattening some shadows while deepening others. The techniques passed down through generations of artists would be adapted to this more complex environment, finding beauty in complications we've never had to navigate. Sculpture would be fascinating. Here, sculptors consider how their work will look under changing light. Morning sun, noon sun, evening light, indoor lighting. But under two suns, a sculpture could be designed to look completely different, depending on which sun or suns are illuminating it. One form revealed by the orange dwarf alone, another form by the red dwarf, a third form when both light it together. The sculpture itself becomes a commentary on perspective, on how what we see depends on how we're looking. Architecture would be functional art in new ways. We talked earlier about buildings designed for shade and thermal management, but they'd also be aesthetic statements. Windows positioned to catch specific combinations of sunlight at specific times. courtyards that create dramatic shadow plays when both suns are overhead, facades that look entirely different when lit from the east versus the west, because the light sources themselves are different colours. The whole built environment would be a response to dual stars, not just practically, but artistically. Buildings as canvases for dual sunlight, changing appearance throughout the day as the suns move through their dance, never looking quite the same twice. Now let's talk about mythology, because this is where things get really interesting. Every human culture has sun mythology. Ra, Apollo, Amaterasu, Surya, Inti, deities associated with the sun, stories explaining its movement, its power, its importance. These myths shape how we think about order, about time, about the divine. They're fundamental to human meaning-making. But what stories would emerge if there were two suns? Perhaps they'd be partners, two gods working together to sustain the world, equal in importance, complementary in nature. One god of beginnings, the other of endings. One of growth, the other of harvest. One of dawn, the other of dusk. Their cooperation explains why the world exists, why life thrives. When they work in harmony, times are good. When they drift apart, when they're on opposite sides of the sky, there's tension, challenge, the need for balance. Or perhaps they'd be rivals, two gods competing for dominance, and their contest explains the variable light. When one sun is brighter, that god is winning. When they're equally bright, the competition is balanced. Eclipses, one sun passing in front of the other, become dramatic moments in an ongoing cosmic struggle. Humans might choose sides, worshipping one sun over the other, or they might pray for balance, for neither god to become too powerful. Or perhaps they're lovers, perpetually chasing each other across the sky, sometimes close, sometimes far, their relationship explaining the patterns of light and heat. When both suns are up together, the gods are reunited, and the world celebrates their love. When one sets while the other rises, they're separated, and there's a melancholy beauty to the twilight. The rare darkness when both are down becomes sacred, the moment when both gods rest, when the world pauses, when humans should also rest and reflect. The possibilities are endless, and each culture would develop its own interpretation based on what they value, what they fear, what makes sense of their experience. But all of them would be more complex than our single sun mythologies, because the sky itself is more complex, offers more to interpret, more to weave into narrative. Religion under two suns might develop differently too. Monotheism has to grapple with how one god creates or controls two suns. Dualism, the idea that there are two fundamental forces in the universe, often good and evil, would seem more natural when your sky contains a visible pair. Philosophies of balance, of complementary opposites, of yin and yang, might emerge more readily. Prayer might be addressed to both suns. Morning prayers when the first sun rises, different prayers when the second one joins it. Evening prayers as each sets. The liturgical calendar would be enormously complex, tracking not just yearly cycles but the relative positions of both suns, creating holy days based on conjunctions, separations, eclipses. Literature would be rich with dual sun metaphors. Where we say as constant as the sun, they might say as balanced as the twin suns, or as shifting as the doubled light. Where we talk about someone being my sun, meaning the centre of our universe, they might have more nuanced language. You're my primary sun implies centrality but acknowledges other influences. We're like twin suns describes equal partnership, mutual orbit, balance. Poetry would play with the complexity. Verses structured in pairs in call and response, in balance and tension. Love poems about being separated like the suns at opposite end of the sky. elegies about eclipses and overshadowing, victory odes about one light overcoming another. The metaphorical possibilities are richer than what we have with our single sun. Music might be influenced too, not directly. Sound waves don't care about light, but culturally. Compositions in two movements, representing the two suns. Harmonies and counterpoints as expressions of dual sun dynamics. Call and response between instruments as representations of the solar dance. Festivals featuring paired performances, two choirs or two orchestras, creating the musical equivalent of doubled light. And the stories people would tell their children, fairy tales about the two suns, how they came to be, why they move as they do, what happens during darkness, perhaps stories about a time when there was only one sun, and how lonely and simple it was until the second sun was born or created or arrived from elsewhere. Or stories about what would happen if one sun disappeared. Scary stories, cautionary tales, myths that teach children to appreciate both lights. Children's games would incorporate dual suns, not just shadow tag, but double shadow tag, where you have to avoid both shadows. Not just sundial, but twin dial, where you track both suns' positions. Not just sunflower, but watching which sun different flowers turn toward, learning that even plants might choose favourites. Coming-of-age rituals might involve astronomical observations, proving you understand the complex movements of the suns, being able to predict when both will be overhead, when eclipses will occur, when the rare darkness will fall. In a world where this knowledge matters practically, for agriculture, navigation, timekeeping, it would also matter ceremonially. History would be measured differently. We date events by years, counting from some significant moment. They might date events by cycles, complete periods of the sun's orbital dance, or by which sun was dominant when an event occurred. In the age when the red sun stood high at midday means something specific about climate, about light patterns, about conditions. Historical records would need to include astronomical data to make sense of what happened when. Philosophy would grapple with duality as a fundamental feature of reality. Is unity possible in a universe structured around pairs? Does the existence of two suns suggest that all truth is relative, all perspective dependent on position? Or does it suggest that balance is the ultimate good, that neither too much nor too little light is ideal? Ethics might be influenced. If the universe itself demonstrates partnership, two suns working together, perhaps moral systems would emphasize cooperation over competition, balance over dominance, harmony over conflict, not deterministically, but as a natural framework for thinking about right action. Or perhaps the opposite. Perhaps the constant need to manage dual sun conditions would create more individualistic ethics. Everyone responsible for their own survival, their own heat management, their own adaptation. The universe doesn't coddle you with simple conditions, so neither should society. We can't know. What we can know is that the stories would be different, the metaphors would be different, the meanings people make from their environment would be shaped by that environment, and an environment with two suns offers different raw material for meaning-making than our single sun provides. And this matters because stories aren't just entertainment. They're how we understand who we are, where we come from, what our place in the universe means. A civilization under twin suns would tell themselves into being using different stories than we tell, and those stories would shape their consciousness, their values, their sense of what's possible and what's important. If we ever make contact with such a civilization, if we find signals from a binary system, if we somehow communicate across the light years, we'd need to understand that their entire conceptual framework is different. Not just their technology or biology, but their stories, the myths and metaphors that make their world make sense. And perhaps they'd be curious about our stories, about civilizations under one sun, about how we make meaning from simplicity rather than complexity, about what it's like to have one unchanging reference point in the sky instead of two dancing partners. Perhaps we'd trade stories, not just data or scientific knowledge, but narratives, the myths of one sun and the myths of two, the poetry of simple light and the poetry of doubled shadows, the fairy tales each civilization tells its children about light and dark and what it means to live under a particular stellar arrangement. Because in the end, what makes any civilization interesting isn't just how they survive, how they adapt biologically or technologically. It's how they make meaning, how they tell stories, how they understand their existence, not just mechanically, but mythologically, metaphorically, narratively. And a civilization under two suns would tell stories we've never heard, sing songs we've never imagined, pray prayers we can't quite understand, make art that uses a visual vocabulary we don't possess. Their stories would be as different from ours as their sky is from ours. Not better, not worse, just different, just other, just another way of being human, or being whatever they are, under whatever stars they were born beneath. We have one sun, they would have two, and both would give rise to stories, because that's what conscious beings do. We tell stories, we make meaning, we create narratives that help us understand our place in the cosmos. The stories would be different, the meanings would be different, but the need to tell stories, to make meaning, that would be the same. Because that's what life does when it becomes aware of itself. It looks at the sky and asks questions. It notices patterns and creates explanations. It takes the raw material of existence, one sun, two suns, however many suns, and weaves it into narrative. Stories under twin suns, different from our stories under one sun, but still stories, still meaningful, still beautiful, still human or alien, or whatever form consciousness takes when it looks up at a binary sky and wonders why. And so we return. We've journeyed through multiple scenarios, imagined doubled light and complex shadows, explored distant companions and close binaries and figure-8 chaos. We've met black forests and triple shadows and civilizations that measure time by twin sun cycles. We've discovered real circumbinary planets and imagined the stories their inhabitants might tell. We've explored what we'd lose and what we'd gain, what would be challenging and what would be beautiful. But now it's time to come home, back to reality, back to simplicity, back to the one sun we actually have. Because here's what's true. The sun is still there. Right now, as you listen to these words, our single faithful star is doing exactly what it's always done, fusing hydrogen into helium, radiating energy across 93 million miles of space, warming Earth's surface, driving weather patterns, making photosynthesis possible, being the steady, reliable constant at the center of everything we know. Tomorrow morning, it'll rise. Just one sun climbing over the eastern horizon, following the path it's followed for billions of mornings before this one. Not two suns in complex dance, not variable light from orbital mechanics, just one simple, predictable sunrise. And that, having explored the alternative, seems like something worth noticing. We spent all this time imagining more suns, more light, more complexity, and in the process we learn to appreciate what we have. One sun, singular and sufficient, simple and elegant, faithful in a way we rarely acknowledge because its faithfulness is so complete we take it for granted. There's beauty in that simplicity, in having one clear reference point, in knowing that day follows, night follows day, in a rhythm so reliable we literally set our clocks by it, in having seasons that repeat, predictable and regular, year after year, in being able to look up at the night sky and see the stars, really see them, because our one sun has set and darkness has fallen and the universe reveals itself. These aren't small gifts. They're the conditions that allowed life to emerge, intelligence to evolve, civilization to build. The predictability meant our ancestors could learn patterns, plan harvests, navigate by celestial markers. The simplicity meant they didn't need to solve complex three-body problems just to understand when to plant crops. The darkness meant they could wonder about the cosmos beyond their immediate experience. One sun gave us all of this. Not because it's special, we've learned that binary systems are actually more common, but because it's sufficient, because sometimes, often, usually simple is exactly what you need. Tomorrow, when you see sunlight, maybe you'll notice it differently. Maybe you'll see it not as default background condition, but as specific circumstance. One sun, not two. Rising in one direction, setting in the opposite. Casting one shadow per object. Providing one quality of light that changes gradually through the day according to angle and atmosphere, but remains fundamentally one source. Maybe you'll appreciate the ease of it, the way you don't need to track two celestial objects to know what time it is, the way darkness actually means darkness, not just one sun down, but the other still up. The way your mythology can be simpler, your timekeeping more straightforward, your navigation less complicated. Or maybe you'll appreciate it in a different way. Maybe you'll think about these real circumbinary planets we discussed. Kepler 16b, Kepler 47c, all those worlds orbiting twin stars. Maybe you'll wonder if life exists there, if someone is looking up at their two suns and imagining what it would be like to have just one. Maybe you'll realize that what we have, this specific arrangement, is just one possibility among many, and that makes it more precious, not less. Because that's what this thought experiment was really about, wasn't it? Not making us wish for something different, not suggesting that two suns would be better or worse, but helping us see what we have more clearly by contrasting it with what we don't have. Gratitude through contrast, appreciation through imagination, noticing the familiar by exploring the strange. We have one sun. It's been there every day of your life. It was there for your parents' lives, your grandparents' lives, every human who's ever lived. It's been there for 4.5 billion years. It will be there for 5 billion more. On any time scale that matters to us, it's eternal, unchanging, faithful. And yet we rarely think about it. We rarely look up and consciously acknowledge, there it is, the sun, our sun, the thing that makes everything possible, the reason we exist at all. Perhaps that's natural. Perhaps that's how attention works. We notice what changes and overlook what stays constant. But perhaps, having taken this journey through the possibility of two suns, we can return with fresh eyes, with the ability to notice what was always there. The sun isn't just a ball of fusing hydrogen 93 million miles away. It's the reason water stays liquid on Earth, the driver of weather and seasons, the energy source for almost all life, the central reference point for time and direction, the inspiration for countless myths and meanings, the one constant in a universe full of change. And it's ours, not because we own it or control it or did anything to deserve it, just because we happen to orbit it, happen to exist within its habitable zone, happen to be positioned exactly right for life to thrive. That's luck, or chance, or divine providence, depending on your framework, but whatever you call it, it's what we have. One sun, simple, singular, sufficient. That's not a lack. That's not something missing. That's our reality, And having explored the alternative, having imagined the complexity of two, we can return to one with deeper appreciation. So tomorrow, when the sun rises, and it will rise, predictable as always, faithful as always, maybe take a moment, step outside if you can, feel the warmth, notice the light, observe how shadows fall, watch how the sky changes colour as the sun climbs higher. And remember, just for a moment, that this is specific, that somewhere in the universe there might be worlds with 2 suns, 3 suns, complex stellar arrangements we haven't even imagined, that our simple single-sun reality is one possibility among many, and that we're lucky to have it, not because other arrangements couldn't support life. We've learned they could, not because our arrangement is superior. We've learned that different isn't worse, just different, but because this is what we evolved for. This is what shaped us. This is what our bodies, our cultures, our consciousness are built around. One sun rising, one sun setting, day and night in clear distinction, stars visible when darkness falls, seasons following regular patterns, time marked by reliable cycles. This is home. This is normal. This is the specific circumstance that made us possible. And having explored what 2 suns would mean, the challenges and beauties, the losses and gains, the complexity and strangeness, we can now see our one sun for what it is. Not inevitable, not the only way, but our way. The way that worked. The way that allowed intelligence to emerge and wonder about itself and imagine alternatives. If you've enjoyed this exploration, I'd be ever so grateful for a gentle like, and subscribe to join me for more cosmic journeys, and to help others discover these late-night wanderings through space. This is the Sleepy Astronomer, wishing you good night, wherever you are, and may you greet tomorrow's sunrise with fresh eyes and grateful heart. Sleep well under your single star. Dream of twin suns if you like, of doubled light and complex shadows, but wake to reality. One sun, rising alone, perfect in its simplicity, and that perhaps is all we need.